let's go from current slide. And before we actually get going, I have a couple of announcements. The first one, don't know, there's a good chance we'll hear it today, possibly not, but I would think if they're going to do it, we'll probably hear it today. I was told this morning that all day long they're going to be testing the fire alarms. So it's not a drill, it's not a practice your evacuation, it's just they're testing the fire alarms throughout the building. So don't go anywhere. It's not going to be a fire, we hope. If it is, then someone will be running up and down the hall. This is not a drill, this is a fire. Okay, hopefully that won't be happening. So that could happen anytime this afternoon. They said it would be off and on all day today. So far, I haven't heard a single one. They said they had some out in the new part of the building. They were testing that part, but I haven't heard any, okay? So it's a good chance it will happen this afternoon. Don't panic. Don't go anywhere. It'll just be tests, not for us, but for the system. The second of the announcements is not next week, but the following week is Cougar Connection Week. And there's going to be several events planned on both campuses, all Monday through Thursday of that week. That's the 17th through the 20th. And there will be a variety of activities going on, presentations on both campuses, opportunities for you to volunteer for various projects. There's a whole list of places, nonprofits, and things like this that you can volunteer with. There's also be opportunities for you to join various Lawson State organizations like ambassadors, athletics, fine arts, honors college, PBL, no, I think that's what it is, Scholars Bowl, student government, speech and debate, student support services, or STEM. So there will be lots of opportunities throughout that week, Cougar Connection Week. I understand they probably are going to try to get a blood drive going. So that may be in addition to that.
Blood drive's not for another, won't be until after Cougar Week.
After Cougar Week, okay. And here's Justin. And I apologize that I did not get to call Samford today. I had planned to do it yesterday afternoon, but then I found out, contrary to what they had said earlier, they wanted contracts yesterday. So I had to go, when I had planned to do, things like calling Samford and stuff, I had to run to the Birmingham campus and start working on contracts. And I had a class, and then I had to go home and take care of the dog because my wife had a meeting, and then go back to campus, and I was almost 10 o'clock leaving West Campus last night. So I did not get to call the planetarium. I'll try to do that. If there's a chance this afternoon, I'll try. Otherwise, I'll try tomorrow, if possible, unless they come up with something wacko for us to do tomorrow. And then otherwise, Monday. I knew I've got some office hours on Monday that should be available. But anyway, can't think of anything else. Any questions on anything we've covered so far, or questions about anything? Okay. If you did miss quizzes or tests, which I know a few of you have, be sure that, sometime today, get the labs or tests. Be sure to get the lab and arrange when to do the test. I think Sarah said she's going to do 2 tomorrow, okay, on Birmingham campus. So I've got those 2 in my notebook, in my grade book, so I should have those with me. All right, any questions? Okay, where are we now? We finished chapter 16 last time on Tuesday. We did the lab that goes along with chapter 16, or at least I gave it to you, and I told you there's 3 questions on the lab that you will need to make observations of the moon over some 2-week interval, 2-week period between now and the end of the term. You just got to go outside at the time of night that you know you can go out every night, at a place you know you can get to. You're not going every night, but you can go to any night, at a place you can access and still see the moon and everything. Need to determine where that place is, when you can do it, and then start observing. If the moon's not up at that time, wait and just start checking every night until you start seeing the moon, then start your observations. If you do see the moon, you can start your observation then, but it's a good chance the moon will then disappear for about 2 weeks and then come back again. So you need to make, I think they recommend about 5 to 6 observations over some 2-week period. They don't have to be contiguous 2 weeks, but it's better if they are, but you can have the end of one cycle here and the beginning of another cycle there. That's okay. And you observe every other night unless it's raining or overcast and you can't make the observations. Then you do the next available night and then do every other night from there. So you do it over a 2-week period, about 5 to 6 observations, if you can.
What do you do?
Okay, all that's in the lab, and if you listen to it, I went over it in gory detail. So, yeah, basically, what the moon's doing relative to landmarks around you. You've got to be in the same spot every night, or every other night, okay? And then where it's moving relative to the landmarks, and then where it's moving relative to the stars. Those are the 2 questions, and the third is what the phases of the moon are doing. Is it getting bigger, smaller, full moon, new moon, whatever, it probably won't be a new moon, but a crescent. You describe the moon over that 2-week period. Okay, and there's a chart, you can do that. All right, so we did that, gave you the lab, and then we went over the rest of the lab, which we did in class as a group. Okay, so today, and we got started, just barely got started in chapter 17. So today we're continuing in 17. I doubt if we'll finish 17, but I almost guarantee you we won't finish in time for a lab today. So the last 30 minutes of today will be the test on chapter 16. So if you haven't done your formula and equation sheet or anything you want to write down on a piece of paper, might not be a bad idea to be putting that together. So there probably won't be a lab today, so we'll have class, a big class, long class, and then 30 minutes of test at the end. All right? Any questions? All right. If not, we're in chapter 17, which is rocks and minerals, but actually the way the chapter's put together, it's minerals and then rocks. So we'll do that. And we're right at the very beginning, 17:1, solid earth materials. Now, on the surface of the earth, now of course, 2/3 to 3/4 of the surface of the earth is covered with water, okay? We're not counting the water. Solid earth materials. But beneath the water is solid earth materials. We are talking about those materials. So the whole earth is covered with solid earth materials. It's just that some of it has water on top, okay? Now, when you look at those solid earth materials, you'll see that there's a non-uniform distribution of matter. What do we mean by that? In some areas, like Birmingham-Bessemer area, there's little pockets of iron ore that you don't see in most other areas, okay? Non-uniform distribution, okay? We have, in our area in general, pockets of coal you don't see in other areas necessarily. We have a fair amount of limestone, which is not all that common, but it is fairly common in some areas, but not in most areas. What we don't have is, say, any copper deposits or things like that. So, but other places do. So there's a non-uniform distribution of matter. That's on the solid earth materials. Let's go deeper, okay, much deeper, to the core. And this is a molten core. Does anyone know what molten means? Melted. This is a melted core containing most heavy elements. The most predominant are iron and nickel. Okay, that's the molten core, very deep. there's a lot of the Earth that's not the core and not the crust. We're not going to talk too much about that. Most of the rest of it is much like the core. Okay? Then we get to the very, very thin surface crust, only a few miles thick in many places, which sounds pretty thick to me, but compared to the rest of the Earth, that's pretty thin. These are mostly lighter elements. The heavier elements down low in the core and near the core, and most of the lighter elements are in the crust. Like I said, we're one of the few areas that do have little pockets of iron in the surface crust. Okay? Now, 8 elements, 8 out of 108 elements or so that we know about, 8 elements make up 98.6% of the crust. That's a huge amount. Okay? And then rocks and minerals make up the solid crust materials. Okay? That sort of doesn't seem to fit with this, but it's okay. So here is the diagram of what they're talking about here. They sort of got them backward. The crust is illustrated here, and then the whole Earth is illustrated here. Not just the core, but the whole Earth. So let's look at the solid Earth materials in the Earth's crust. The predominant element found there is oxygen. Wait a minute, folks. Time out. Is oxygen a solid Earth material?
No, it's a gas.
We think of oxygen as being a gas, and it is. Pure oxygen. Okay? But you see, the crust of the Earth is made up of all kinds of compounds, minerals, things that are put together, and the vast majority of those have oxygen in them. The solid Earth material. Let me give you just a few examples. I just mentioned limestone. Limestone is mostly calcium carbonate with some magnesium carbonate. Well, calcium, we know what that is, and magnesium, we know what that is. Carbon, we know what that is, and carbon, we know what that is. But what's that 8? Let me give you the example. Calcium carbonate is Ca for calcium, C for carbon, O3. 3 oxygens in every molecule of calcium carbonate. More than calcium and more than carbon, okay? The oxygen is part of that solid Earth material. Magnesium carbonate, Mg, CO3. Again, more oxygen there than in magnesium or carbon, okay? How about sand? Most of the time that's silica. Silica is what we call it. It's actually some type of silicate. The 8, oxygen. That's silicon 1, 4 oxygens. Okay? There's oxygens all over everything, okay? Sulfates. 1 sulfur, 3 oxygens, okay? So many of our minerals are made up, and that first one that we talked about, they said this is manganese carbonate. Again, 1 manganese, 1 carbon, and 3 oxygens, okay? Just not all, but huge numbers of our minerals and rocks, of course, too, have oxygen as part of the solid material. They're part of the compounds that make up the solid material. So that's why oxygen, this is not gaseous oxygen, this is oxygen fixed in a solid structure that's part of the Earth's crust. Okay? Number 2, and that's almost half of all the Earth's crust has a huge amount of oxygen in it. Okay? More than a quarter have silicon. I just mentioned that. Si. Most of your sands, clays, all those things have, certain amounts of silicon in them. Okay, almost a quarter. So in these 2 alone, more than 3/4, or awfully close to 3/4 of the Earth is just of the Earth's crust, or those 2 elements alone. All those 3/4 of the Earth's crust, those 2 elements alone. After that, aluminum, which is one of the lightest of the metals. Then you get iron. This is, we do have iron in our soils. In fact, Southeast in particular, Georgia is really well known for it. The Georgia red clay. We have plenty of red clay here. What is it that gives it the red color? Iron oxide. Exactly. Rust, basically. And the iron and oxygen, okay? And if it's not in a silicate or aluminate or something else like that, it's also often an oxide, which has large amounts of oxygen in it. So aluminum is there, then iron. Calcium, as I mentioned, we have limestone, which is calcium carbonate. We have another mineral called gypsum, that is calcium sulfate, and there's lots of other calcium sources there. But again, it's really low percentage, 3.6%. Sodium, again, pretty low, 2.8%. Potassium, 2.6%. Magnesium, remember I said magnesium carbonate is your dolomitic limestone, and magnesium sulfate is Epsom salts, which occurs in nature too. And everything else, all the other 100 or so elements make up only 1.4% of the Earth's crust. Okay, 98.6 plus 1.4 makes up 100. Okay. Now, if you include the entire Earth, that's most of everything else, but the crust included, then the predominant element is iron. Okay, it's all over in the crust. It's all over in the outside the crust and inside the. In the core, outside the core, anything below the crust is going to have lots of iron in it. Right at a third of the mass of the planet, the whole Earth, is iron. Next is oxygen, mostly from the crust, but also from other places as well. Silicon reduces big time to 15.6, but still a large amount. Magnesium goes up really big because we call the iron and magnesium minerals, we'll call those the ferromagnesium minerals, and they are a big portion of the inner part of the Earth. And after that is nickel. Now, they mentioned nickel here without saying magnesium. Really, I think it should be iron, magnesium, and nickel. But we don't think of magnesium as being a heavy element. We think of it as a lighter one. But still, there's plenty of magnesium in the interior. Okay? Calcium, there was a fair amount of calcium here. You also have it throughout the structure, but it's just not nearly as prevalent as in the crust. Aluminum, more prevalent in the crust, very little prevalence there. And sodium is really, really small there. Everything else, 1.9%. Okay? So, that's the elemental constituents of the solid earth materials. Hardly anything is pure silica, pure oxygen, because if it's pure oxygen, it'd be a gas. Pure manganese, magnesium, the closest would be the iron, okay, in the interior, okay. And around the crust, it's mixed up with everything else, but in the interior, you'd have a lot of pure iron, and pure nickel, and some pure magnesium. But after that, everything else is usually joined with something else, like oxygen. Okay. Now, that was solid earth materials. 17.2 now begins talking about minerals. Okay, we're going to start with the definition, the earth science definition of a mineral. Several features here, every one of them important. Naturally occurring, number one. Inorganic, number two. We'll talk about what that is in a minute. Solid, number three. Either element or compound, it can be either one, with a crystalline structure. Number four, crystalline structure. Okay? Now, naturally occurring means if man had not even been anywhere close to it, it's going to occur. There is a lab at UAB, or at least there was one, that they produce synthetic diamonds. Okay, now diamonds are naturally occurring materials. The lab that produced synthetic ones, those wouldn't be counted as minerals. Though they fit everything else, they're not naturally occurring. They were man-made. So that's what would eliminate that. But believe me, that's a very small amount they make. Okay? Inorganic, what does that mean anyway? Not having come from living material, at least recently. Okay? So inorganic would be non-living source. Okay? So that means not directly produced by a living organism. Okay? Our teeth, solid material, right? But that's not a mineral because that's part of a living being, or at least it is now. Okay? So that would not be a mineral. Though it may have a lot of the other characteristics, the crystalline structure, repeating patterns, but it's coming directly out of a living organism. Okay? And then, I've said the solid, these are all considered solid. Water, of course, even though it's prevalent on the surface, is not a mineral. Okay? It may dissolve some minerals, but it is not a mineral itself. Okay? It could be element or compound. But then this thing about a crystalline structure. Okay? That means it has a regular repeating pattern. Okay? And crystalline structure. It doesn't have to be a real pretty crystal like we saw at the very beginning. It could be just a plain old crystal of some nature, but it has to have that regular repeating pattern. The example they give here is halite. That's a naturally occurring mineral. Okay? So that is a mineral. What is it? What is sodium chloride? What do you usually think of that as?
Salt.
Salt. Okay? Table salt. But that table salt may or may not be generally not a naturally occurring mineral because that's been processed. It's been synthetically refined and made into a crystal structure and everything else, but it has been modified. Halite is naturally occurring sodium chloride. And this is how it looks. There is one error on this slide. They corrected it in the book, but they got it wrong on the slide. Okay? We'll see it in a minute. Now the sizes aren't correct. Okay? This is a sodium ion, which is a positive ion, and so typically it would be smaller in size. This is a chloride ion, which is a negative ion, so it would be larger in size. They aren't dealing with the size here, they're just showing the distribution. Every sodium is connected to only another chloride, and every chloride is connected only to a different sodium. Okay? Does anyone see the error in the slide? That one right there. This should be a chloride because it's connected to two sodiums. So that has to be a chloride. In fact, 3 sodiums, that one up there. So that should be a chloride. They got it colored wrong. Your text is correct. Okay? This is it. Now, what kind of structure is that? A cube. And that's what it's called. A cubic structure. And that's the repeating element. Every one of those little cubes repeats that same pattern. That is a cubic structure. Okay? If you were to take your table salt, sprinkle a little on probably a black piece of paper or felt or something like that, get you a good strong magnifying glass and look at those crystals, you'll see most of them are nice little cubes. Okay? Very nice little cubes. That's the repeating pattern of halite. Now, that's just one pattern. There's tons of different patterns out there. That's one of the simplest ones. Okay, and you'll never see a sodium and a chloride ion. They make up the cubes like this. Zillions of them making up one cube. That's probably an exaggeration, but not bad off. So, what do we mean by these crystal structures? Okay, wait, time out. There's a little thing here myths, mistakes, and misunderstandings. Okay? This author does not care for some of these things such as healing crystals. Okay? Now, maybe some of you are into these, and that's perfectly fine. But you can tell this author doesn't hold much credence. No scientific studies have been found that these are beneficial. So I'll let you read that on your own. So let's move to crystal structures. This is on page 439 after a pretty picture of a salt shaker. And you can almost see those little cubes on it because it's blown up a little bit. This is crystal structures. Can be made up of one or more kinds of element. For instance, diamond, I mentioned that earlier, is one and only one element in a pure diamond, and that's carbon. Carbon? Okay. What do you usually think of when you think of carbon?
We breathe it out.
Is what?
We breathe it out.
We breathe out carbon dioxide, so it can be a gas when combined with oxygen. But if you think of pure elemental carbon, you ever think of that? What I think of is soot. That's carbon. I think of carbon as being black, okay? Dark colored. Diamond is not black. It's not dark colored, okay? But it's made out of pure carbon. In fact, if you were to take, and this is what they do in that lab at UAB, they take pure carbon, which is probably, you got several forms you could have, but soot, it's pretty close to it. Coal is not pure carbon, but it has high concentration of carbon, which is black and gooey stuff. Any of those things. Graphite is pure carbon, okay? And it's definitely not a diamond, okay? But you submit that to enormous temperatures and enormous pressures, and you produce diamond. And it changes because of the molecular fields or the molecular bonds and atomic bonds that you have. You change those and make it into diamond. It changes its color, it changes its hardness, it changes everything about it. So that's pure carbon. Whereas quartz, think of your little sand grains that get in your shoes and bother you, and you feel like it's this big and it's really just a tiny little thing. That's silicon and oxygen. So that would be made up of two different elements, okay? So that would be a compound. This is an element, these are compounds. Again, a beautiful crystal structure, and we'll see pictures of it coming up. Now, we classify these crystal structures based on what we call the surface symmetries. How do they appear to be? And they show 6 major systems. I'll tell you right now, don't sweat these. I'm just showing them to you to show you the differences you see. You're not going to be asked to identify these or separate or pick them one out from the other. I'll just tell you what these are. 6 major systems: isometric, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. Okay? And they're going to show you some illustrations of this, and I'll try to describe as much as I can, but there are some of these, especially these two, I have no clue of why they name them this way. Okay? But we'll get there. Okay? Here's a picture of it. First, a whole bunch of different isometrics. Now, does anyone know what the prefix, well, let's do the suffix first. Suffix metric means. Second? Okay, well, measure. Whatever you're measuring. This is a measure. It could be distance, it could be, and in fact, that's pretty close to what they're really meaning here. But iso means same. Same measure. In other words, every dimension on an isometric crystal is the same. Okay? And here's the first of those. A cube. This was our halide, sodium chloride. One atom at each corner. All the lengths are the same. You're saying distance. All the lengths are the same. That's what makes it a cube. One here, 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 here. All those measures are the same. Now, this one looks shorter here, here, and here. They're really not. It's just three-dimensional on a two-dimensional board. It's kind of hard to do. If you twist it around, you see those are the same. Okay? So a cube, like your halite crystal. Here's an octahedron. What does that mean? Octa means 8. Okay? Hedron means sides, basically. 8-sided crystal. And here's what you got. 1, 2, 3, 4. 1, 2, 3, 4. There are 4 triangles, equilateral triangles, put together in such a form, 8-sided figure, octahedron. This is a 6-sided figure, 1, 2, 3, 4, 5, 6. 8-sided figure here is an octahedron. All the lengths are the same, and I believe pretty close to, maybe not quite all the angles are the same, but pretty close. The similar ones are. Octahedron. This is a tetrahedron. Tetra means 4. 4 sides. There's a side, there's a side, there's a side, there's a side. 4 sides, all, I think, pretty close to being equilateral triangles, meaning equal lengths. Every one of those bond lengths are the same. Okay? So that's a 4-sided figure. Tetrahedron. 8-sided figure, octahedron. And this, it's sort of hard to visualize. It almost looks like it's sinking in. It really is popping out, kind of. This is a dodecahedron, or something like that, meaning a 12-sided figure. Okay? Now, actually, I'll look at this, and Zachary's here. Oops, let me get in the right class. All right. I probably shouldn't, probably not the same, but I think of a soccer ball. Okay? Possibly a volleyball, sort of. It has, it's made up of different patches. All those patches are about the same, but it is a spherical shape, but the patches almost make it seem like this. That's a 12-sided equal length. See this length? That looks like a little cube right there, but part of that's interior, part's outside. That looks like another one there. But every one of those is equal length, isometric. Okay? Hexagonal, what does that mean? 6-sided. Okay? These are 6-sided structures that are not cubes or other things. This is a hexagonal prism. Prism means it has uniform dimension one way and then you're designed the other way. So every cross section of this is a prism. 1, 2, 3, 4, 5, 6. 6 sides. 6 sides of this going up and down. We're not counting the top and bottom, but 6 sides that way. That's a prism. Hexagonal prism. This, frankly, looks a lot like this, only they're not equal in size. This is a rhombohedron. Now, the other difference here, I don't know if y'all know what a rhombus is. If you picture a square, which is equal side length and equal angle, all right angles, that's a square, and you sit on it, okay, and it sort of squishes over this way. Still equal length, but now not equal angles. Some of them are acute angles, some of them are obtuse angles. A rhombohedron, okay, a rhombus is a square that's been sat on. A rhombohedron is sort of like a cube or any kind of a 6-sided figure that has been sat on, and now the angles are not equal. So unequal sides, and not all sides are unequal, but not all sides are the same, I'll put it that way. And also the angles are not right angles like they have here. That's a hexagonal. Why is it hexagonal? 6-sided figure. Okay, just like I said, this is a 6-sided figure with all equal angles and equal sides and equal angles. These are just not equal sides or angles, but still a 6-sided figure. So that's hexagonal, not isometric. Okay, tetragonal. This is a 4-sided figure. And this is what I think most of your quartz, which is silica, is basically kind of a tetragonal type structure. Four-sided figures, and it may have triangles, it may have rectangles, whatever the sides are of that. And that is a prism, again, a uniform height, but symmetric about one axis, and everything else is symmetric about that. Now, orthorhombic. What's the difference in a rhombohedron and orthorhombic? I have no idea. Okay? Orthorhombic again means not necessarily the same angles, usually the same length of sides, but not necessarily equal angles. And orthorhombic, as opposed to rhombohedron, I can't tell the difference. I don't know. There has to be a difference. I just don't know what it is. That's a prism that is an orthorhombic prism. Okay? Monoclinic, to me, monoclinic means one something. And I can't figure out what's one something about this. It is a prism, and I think the deal is none of the sides have to be equal. Maybe one side is equal to itself, and that's about it. So I don't know. I'm just guessing on that. And then that's a triclinic. I look at that and say, what's the difference in that, orthorhombic or a rhombohedron? They all look somewhat similar to me. So I can't tell you anything. But again, you don't need to know this, but just to get an idea what a variety of crystal structures you can have. Okay? They can come in all kinds of shapes and sizes and dimensions and other things. There are certain features to be classified in one of these that have to be the same. Like the isometric, all sides have to be equal. Okay? Hexagonal has to be six-sided somehow. Tetragonal has to be four-sided somehow. And the others, I'm sure, have some type of meaning. I just can't, just from the pictures, can't figure out what they are. Okay, so those are your samples of crystal structures. All right. Here are some pictures of crystal structures. Now, your book doesn't have this particular picture anymore. Now, what they've done, they used backlighting with color so you can see these things easier because they're clear. If you just had white light in the background, they're almost invisible, okay? But that is a perfect looking little cube. Looks like the edges have been rounded off, which they probably have. And every one of those is a cube, just looked at from different angles. And that is the structural unit for the crystal of table salt, sodium chloride, whose mineral was halite, okay? It's cubic. And you can see from those individual grains, every one looks like a little perfect cube. Now, some of them look like the cubes could have been fractured, which they probably were, because they grind this down so it'll all go through the holes in the clay. And so there has been some modification to that, but that's an example of that's halite. Over here, these are quartz crystals. Now, they're not all pure and perfect crystal, but here's the one. I can't tell if that, I said they were tetragonal. They may be hexagonal, because it looks like this could be six-sided, not just four-sided. But look at that. And what we call this are cleavage planes, where the breaks out. You see, there's a plane, there's a plane, there's a plane. Here's a plane, here's a plane, there's a plane. You see planes all over. So these are quartz crystals. Oh, and these are hexagonal prisms. Okay, I said it wrong before. Hexagonal prisms. And there's a real pretty one. It seems like it's just stuck on. Smaller ones here. Here's the end of some here. And there's some there. When we get to lab, won't be today, it'll probably be Tuesday, depending on when we go to the planetarium. While y'all are doing your lab, I will be setting out and so you can look at various crystals, and you can see some of the rocks that contain quartz crystals. And my goodness, those things are pretty. Okay, you can see those hexagonal shapes in there, and they just are rather gorgeous. Okay, just how nature made them that way. You know. So those are samples of crystal structure. All right, now how do we classify the minerals, especially found in the crust, the Earth's crust, where we live? Remember what the two most predominant elements were? And silicon. Okay, oxygen and silicon. And those go together to make silicates. The ATE means oxygen combined with it. And silicate is SiO, I think I said O4, I believe that's right. Could be SiO3, I believe it's SiO4. Lots and lots of oxygen in it. With some silicon, but lots of it. Contains mostly silicon and oxygen. The cation that goes with that could be something else. Sodium silicate, magnesium silicate, something like that. But that's little compared to the silicate part. Makes up 92% of the Earth's crust. Silicates make up 92% of the Earth's crust. It means all the other minerals added together, only 8%. Silicates are 92%. Based on the silicon-oxygen tetrahedral unit. I knew that was in there. And that sounds, okay. Quartz crystals, which are silicates, are octahedral crystals. But they're based on a tetrahedral unit that goes together to make them. I mean, hexagonal unit, crystal. And that sounds contradictory, but it really does work. Okay, here's the deal, and I think they're going to show one. Yeah. Now, the size is not precise here. Silicon, because it's a 4 positive, +4 ion, it is tiny. And here's why I say that. And earlier I said it about sodium and chloride. Sodium ion is small, chloride ion is bigger. The positive ions are smaller. What makes up most of the volume of an ion or an atom? It's the electron cloud around it. The nucleus has almost all the mass. I mean, just incredibly dense. The nucleus is. It has protons and neutrons in it, which are very massive. But it's tiny. It is minuscule. And then all the area around there is taken up by electron cloud, and the electrons have almost no mass. They have some, but not very much. 1/10,000th the mass of a proton or a neutron. So very little mass, but they take up the whole cloud around. So if you lose an electron, you become a positive ion. Well, now those other electrons are pulled in tighter because you have more plus charge than you have negative charge, so it pulls them tighter. Whereas when you have the negative things, you have extra electrons in the cloud, now they get further apart because they repel each other. Okay? So your negative ions are huge, volume-wise, and your positive ions are pretty small, volume-wise. And since this is a +4, that's really tiny, and then the 4 big old fat oxygen, which are -2, they're on the corners. And these make the tetragonal unit. Now you put a bunch of these together and you get your quartz crystal, which is hexagonal, not tetragonal. But each unit is tetragonal. So that's why they say unit, not crystal, tetragonal unit. Okay, tiny little silicon in the middle, and then 4 oxygens at the corners. That's your tetrahedron. 1, 2, 3, 4 sides. All equal. Okay. Now, how do these go together? Well, you have some isolated tetrahedrons. Okay. Probably not a huge number, but you do have some. Okay. Then you have chain tetrahedron, chain silicates. So here's your isolated tetrahedron. That's that little silicon in the middle. Now this is much better size-wise. The little green silicon in the center, these big fat 4 oxygens around on each of the points of the tetrahedron. Okay, so an oxygen here, there, and there. Okay, and these are your isolated tetrahedrons. Those sizes are much more the scale than what the others were looking at. The chain silicates, what they do here, one bond here is shared with another bond. Actually, they're showing points being shared, which I guess could happen as well. That point is that oxygen. So take out one and connect it to, or have one being shared by 2 silicates. So now you have fewer oxygens because some have been replaced, and you have this chain type silicate. There are some of the minerals, clay minerals. Halloysite is one. Some of your asbestos minerals like serpentine and others like that are chain silicates like that. Okay? The third kind is what we call sheet silicates. So that is a bunch of silicas combining together, and now this, say one of these oxygens here is now being shared by this one and this one over here, and this one shared. Okay, so here it's just one oxygen is shared between 2 adjacent ones. Here, one oxygen is shared between 2 adjacent ones. Okay, so that is your sheet silicates. And then you have what they call the framework silicates, where you don't just have them in sheets, but you have them in 3 dimensions. And that would be more like your quartz crystals would be framework silicates. So you get 3 dimensions, not just 2 dimensions. Now the 2 dimensions, I mentioned halloysite is a clay mineral. Some of your asbestos, serpentine, and some of those others are chain type. Your sheet type would be many of your clay minerals like kaolinite, montmorillonite, bentonite, several of those. The silicas come in sheets. Now usually they also alternate with alumina sheets. So it's not just all silica, but silica, alumina, silica. That would be, say, bentonite or montmorillonite. Silica, alumina, that would be kaolinite. Okay, just some minerals. And they do a fair amount of kaolinite mining. I know over in Georgia, they probably have some here in Alabama as well. Since we're so close, you would think there'd be some here. I know in Georgia there's several pretty good-sized kaolinite mines. Anyone have an idea what we use kaolinite for? There it is. This pencil. The black in the pencil is actually graphite. I mentioned it earlier. That's pure carbon. But it's black, like soot. But pure graphite is really, really soft. You'd have a hard time writing with it. So to harden it up, they mix it with kaolinite, which is a clay mineral mined in Georgia and other places like that. And the harder the lead, the more kaolinite. The softer the lead, the more graphite. Okay? So that's what makes pencil lead. This is the number 2, which has a pretty good mix. Number 1s are really soft. Number 3s and 4s are really hard, much more kaolinite in it. Okay? Now, in order to get that to write on paper well, they generally will put a very thin coat of kaolinite on the paper. And the kaolinites, that will do pretty well. However, if they get too much kaolinite on the cover, on the paper, you get this really shiny thing, like magazines and stuff that have that real good sheen. Kind of hard to write on that, okay, because there's too much kaolinite there. So kaolinite is used to give you a glossy kind of a surface, okay? Now, kaolinite, clay mineral, very tiny, tiny, tiny mineral. I don't know if when you were younger, if you had an upset stomach, mama or grandmama gave you Kaopectate. Anyone ever hear of that? Probably not. They don't use it much anymore. How about Pepto-Bismol? Okay, that's got some things like kaopectate. You know, that's sort of a...
So it was like gritty, like chalky.
Yes, it's a very much a chalky kind of thing. Those minerals are so tiny and they're very reactive, so they absorb that stomach gas or stomach acid and stuff like that that's making your stomach upset. Absorb it. Sometimes it will stop you up, but you know, it keeps it from proliferating. So kaopectate, the KO in there is from kaolin. Okay, kaolinite. All right, those are sheet silicates. Okay. 92% of the Earth's crust made up of the silicates. You also have then the other 8% are non-silicates. No silicon-oxygen tetrahedrons anywhere in the crystal structure. Okay? Only 8% of the Earth's crust. Why do we spend much time with them? Well, they're pretty important. 8 groups of those non-silicates, and these are generally listed in by their abundance. The most abundant, but still not very big, are your carbonates. Now, I've already mentioned some carbonates. What were some of those? Limestone. Much of Alabama, the bedrock, the parent material underneath the soil is limestone. We have a lot of limestone here. Poor old Georgia next door is mostly granite, okay? Acid igneous rock. We'll talk about that a little bit later. Granite usually doesn't make very fertile soils, I'll say, okay? It's just, and that's why they call it acid rock. Carbonates, on the other hand, really great soils. That's why the agriculture in Alabama probably is better than that in Georgia, okay? Very abundant of the non-silicates, and these are the carbonates. Instead of SiO4, they are CO3s, okay? And there are 2 major types of these, the calcium carbonate, which we call limestone, and the magnesium carbonate, which when you combine with calcium carbonate, you have dolomitic limestone, or dolomite. Calcite is the mineral that's calcium carbonate, and dolomite is a mineral that's calcium and magnesium carbonate. Then you have your sulfates. This is SO4, okay? SO4. I believe that's right. Yeah. And those are your sulfates. Most common of those would be calcium sulfate, which is also called gypsum, and magnesium sulfate is, I just said it a few minutes ago, Epsom salts, okay? Then your oxides. There's lots of these oxides out there, but they're usually really, really small, okay? For instance, those clay particles that we talked about, that kaolinite, it's white. It's colorless. It really doesn't have any color to it. Most of the clays you see are red, okay? Though some are orangey and yellow and stuff like that, but most of them are red. Well, what the clay, which is incredibly tiny little particles, is coated on the surface with iron oxide. So the clay itself is colorless, but the little bit of iron oxide on the surface makes it look red, okay? So those are your oxides. Iron oxide, you have aluminum oxides, you have most of those other elements you saw there in oxide form. Similar to oxides are sulfides, okay? These contain absolutely no oxygen. These have oxygen. Your silicates have oxygen. Your carbonates have oxygen. Your sulfates have oxygen. Your oxides certainly have oxygen. Your sulfides do not. That should be something like calcium sulfide, sodium sulfide, you know, just something with sulfur. That's it, just those 2. We'll talk about one of these that is fairly famous in a little while, but we'll come back to it. Halides. One example we've already talked about. Halite with sodium chloride. Now let me tell you where the halide comes from. A little bit of chemistry here. Your first column here in the periodic table, these are called your alkali metals. They're pretty soft metals, most of them, but they're alkali metals. Now, hydrogen just stuck there on top is a gas. It's not a metal at all. And then you have your alkaline earth metals here. There's your magnesium and calcium in there. Then you have your transition elements here. These are what we usually think of as metals, the harder metals that form metals. Then you get to nonmetals and things in between here. But that seventh column here, these are your halogens. The halogens are where the halides come from. Something fluoride, something chloride, something iodide, something anything with it, something bromide, anything like that are going to be your halides. Sodium chloride, salt, halide, magnesium chloride, calcium chloride, magnesium fluoride, any of those that have this as the second element. Then finally, number 8, these are called noble gases. Noble in that they don't mix with anybody. They're aloof. And the reason is their outer electron shell is completely full, doesn't want any more electrons, doesn't want to lose any electrons, so they don't combine with anything. Helium, neon, argon, krypton, xenon, radon. Okay? Those are noble gases. Even radon, as heavy as it is a gas. Doesn't combine with anything. Okay, so let's go back. These have just one electron in the outer shell. That's why they're real easy to lose. That's why you have sodium as a positive ion. It lost that electron. Potassium, positive ion. Lithium, positive ion. It's easy to lose that outer electron. These would have to lose 2 electrons, but they do. Beryllium, magnesium chloride, calcium chloride, they lose 2 electrons. Okay, they really get tight. Okay? These transition elements share electrons. They don't typically gain or lose them, they just share them. These tend to pick up electrons. That's why these are so active over here. Fluoride, these have 7 in the outer shell, they want 8, they'll steal electrons to get that outer shell. But then they become ions, negatively charged, and they get a little fat. Actually, really fat because it gains 2 electrons. These have 8 in the electron. They don't combine, they don't gain, they don't lose. They are just float around by themselves and don't interact with anything. Okay, so those are your halides. They are combined with something in column 7. Then you have your phosphates. Go back to your 8s. This is phosphorus with oxygen. PO4, phosphates. Okay? Hydroxides. Rather, oxides are H's. Okay? You have hydroxides, which is OHs. H for the hydrogen, O for the oxygen. The OHs, these are hydroxides. Aluminum hydroxide is one pretty well-known, and there's several others. And finally, you have your native elements. I mentioned these earlier. This would be your iron ore, your copper ore, your silver ore, your gold ore, your whatever metals that just exist by themselves. Okay? Those are your native elements. Okay? The most rare. That's why they're pretty valuable most of the time. Okay? So these are your non-silicates. Only 8% of the Earth's crust, but they have no silicates. Everything else has silicates of some kind in them, and these are your silicates, SiO4s. These don't have. Now, let's look at the combination of these, silicates and non-silicates. This is a table that shows them all, okay? All your minerals in the Earth's crust are split into silicates or non-silicates. 92% over here, only 8% here, okay? Very unbalanced, okay? Now, in your silicates, you have 3 classifications there. your ferromagnesium silicates. Ferro means, anyone know what it means? Fe, iron. Iron and magnesium, remember they pair up. They're two of the most prevalent elements in the Earth's core, okay? Iron and magnesium. Ferromagnesium silicates. Then the non-ferromagnesium silicates, these are the silicates but don't have any iron in them, or not much iron, okay? And then you have the clay minerals. Now what the clay minerals are, those are minerals that basically they were something else. They dissolved or wore away or something like that, and then reconstituted themselves as very tiny little crystals, and that's what makes them clays. There's your kaolinite, I've been talking about illite, chlorite, montmorillonite, bentonite, bunches of those. So let's focus on these two. The ferromagnesium silicates are those with iron content and or magnesium. Some of these you'll see in later slides: biotite, hornblende, augite, olivine. Generally, this is increasing amounts of iron here. And in increasing amounts of iron, you get darker and darker and darker in color, okay? And usually deeper and deeper and deeper in the mantle that we haven't talked about yet. It's made up mostly of olivines. It's pretty deep stuff. Okay, the non-ferromagnesium, and by the way, ferromagnesium, dark colored because iron is dark. Also dense because iron is heavy. Without the iron in there, they're lighter. Lighter in color, but also lighter in density. Quartz is almost pure silica. Crystal clear most of the time. Occasionally I have a chunk of rock down there that has some pink quartz in it that just has some impurities there, but it makes it look prettier. Muscovite, which is a white mica. And by the way, when this sort of erodes away and wears away, it becomes illite clay. So these are somewhat connected. The feldspars, these are alumina silicates, no iron, but aluminum silicates. And then there's several types of feldspars. One is plagioclase, but that is split into two kinds of feldspar: sodium feldspar and calcium feldspar. Another is orthoclase, and it's potassium feldspar. Okay, so sodium, calcium here, potassium here. These are plagioclases. You don't need to know these and how they break down, but it is helpful to recognize when you see feldspar, no iron. Okay, the clases here, orthoclase and plagioclase, are types of feldspars, and they differ by what their the cations are: sodium, calcium, or potassium. Okay, and then, like I said, the clay minerals are minerals that are broken down, then reformed to be small crystal minerals: kaolinite, illite, chlorite. There are three of them. There are many of them. So look at the non-silicates. We've talked about the classifications before. We'll mention them again: the carbonates, the sulfates, oxides, the sulfides, phosphates, halides, and your native elements. So in the carbonates, again, like I said, the minerals here are calcite, which is calcium carbonate, and dolomite, which is a mixture of calcium and potassium carbonate. The sulfates, calcium sulfate is gypsum. I don't remember what anhydrite is. It seems like that's aluminum sulfate, but I'm not absolutely certain on that. The magnesium sulfate is Epsom salts, so that goes over there too. The oxides, some of the more common ones are hematite, that's iron oxide, rust, okay. Magnetite, which is iron oxide. There is absolutely nothing chemically different between hematite and magnetite. Identically the same. One little difference though. This is magnetic, that is not. This is naturally occurring magnet, lodestone, I don't know, it has several names like that. This is the same mineral, but not magnetic, not naturally occurring magnet. limonite. I'm trying to remember what that is. Aluminum oxide, maybe? No, these are aluminum oxide. Limonite is some other, maybe copper oxide on the top. Limonite. Okay. Sulfides. Here's the one that I can't remember for sure what this is. I think this is calcium sulfide. If not, it's something like that. But it's pyrite. Anyone know common name for pyrite? Huh? No, okay, yeah, from pyrotechnics. That's a good guess, but it's not. Actually, the name of it is, the common name is fool's gold. It looks like gold, it acts a lot like gold, but it's not gold. Gold is a pure element. This is a compound. And a lot of people will mistake pyrite for gold. They, hey, I'm going to be rich. And you got fooled. Okay? It's pyrite. Sphalerite, just another one. Galena, that's usually a high iron sulfide. And then chalcopyrite is, I think, copper combined with calcium or whatever the other one is. Okay? Now, phosphates, there's really only one that I know much about, and that's appetite. It means you love to eat. No, this is an A here, not an E. Okay? Appetite. Now, there's a lot of phosphate mining that goes on down in Florida. Central Florida, I don't know if y'all are familiar, you know where Orlando is and Tampa. About midway between those two, the center of the state is called the Bone Ridge of the state. And the reason it's bone is that it has a lot of marine deposits there. That's where they do a lot of the phosphate mining that mine the apatite. Now, why do they mine the apatite? Well, any of you ever buy any fertilizer for your grass or vegetables or trees or anything? Okay, you notice on there a lot of times they'll have three numbers at the top of the bag. 5, 10, 15, 10, 10, 10, you know, something like that. The first number is nitrogen fertilizer, which is really important for growing anything, okay? Because nitrogen is in every protein that is made. Any protein in your body has nitrogen in it, okay? The second number, I always get these confused, I think it's potassium. Potassium is a primary nutrient for plants. And the third one is phosphate. Okay? Another primary nutrient of plants. Now, actually, plants use more calcium than they do phosphate. But there's plenty of calcium out there. There always is. No matter what your soil is, usually there's enough calcium there. It's just all over the place. But phosphate is not there frequently. And when it is there, it's tied up and it's hard for the plants to get. So that's why we put that as a major soil nutrient for plants, because it's hard to get and hard for the plants to get out. As soon as you put it in the soil, it gets trapped again. You know, so you have to really dump the phosphate to it so the plants can get enough to be healthy. But here's a problem. We have mined most of the readily available phosphate, I would say, that we know of on the planet. Maybe there's some deposits somewhere we haven't found, but there's not many. We have mined and mined and mined the phosphates from Florida and those other places like that. Has anyone heard the term the Green Revolution? This happened pretty much after World War II and up to the current time. There was a point somewhere back there that people were saying, you know, we can't support much more population because we can't feed the people. We can't grow enough grains and grass for cattle and other stuff to feed very many more people. And they thought the limit for world population was probably somewhere down around just a few billion. Well, we got a few billion, and China right now and in India right now. Well, how does that happen? Well, because they found a way to produce more nitrogen fertilizer very easily. It used to be they mined it out of mostly Chile and Peru and some of those places where for millennia bats had roosted in caves, and of course when they did, they pooped in the caves, and that bat guano, got piled up, and that was a great nitrogen fertilizer source. And that's what they did. It was called sodium nitrate. Not too much nitrogen in there, mostly nitrate, oxygen. So it was NO3, sodium nitrate, mostly oxygen. Okay, but we're using that like crazy and running out. And they said we are not going to be able to feed the planet because we need more nitrogen fertilizer. Well, along came a guy, and it was probably several guys, but the one that I knew of most, his name was Franz, I think it was, Haber, Haber. It looked like Haber. For years I called it Haber, and I heard someone pronounce it, and it was Haber, not Haber. Okay? And Franz Haber developed a way to take methane gas, which is pretty prevalent, and basically nitrogen that comes in the air. 80% of the air is nitrogen, but it's not usable. We don't use it, plants can't use it, except for very few. And he was able to come up with a synthetic nitrogen fertilizer called urea, which sounds like what you have in urine. And it really is fairly close to it, except it's very concentrated nitrogen fertilizer. Much more concentrated than sodium nitrate. Way more concentrated. Okay? That's called the Haber process. Basically, that was largely responsible for what we call the Green Revolution. Suddenly, we could produce lots and lots and lots of food, so we could support many more people on the planet. That seems like a pretty important thing to discover, doesn't it? And you would think, surely he won some awards for that, maybe a Nobel Prize in Chemistry. No, he didn't. Wonder why. Say again? No, not that reason. Others, I don't know. I don't think he did. But I don't think that was it. Here's what was it. He was German around the 1930s and 40s. And he was a Nazi. And he was the chemist that came up with these experimental gases that they used on the Jews in the gas chambers. And he was responsible largely for the murder of millions of people. So they decided not to give him any awards, just because of his other. That one process, the Haber process, that would have been enough to earn him accolades everywhere, except for what he chose to do with the rest of his mind and life. So he didn't get any more. So that's really the side point. Okay, what I was getting at with that, because nitrogen, suddenly we had plenty of that, so we could grow more foods. But of the big three, nitrogen's taken care of now. Potassium, we are using it up fairly rapidly, but there's a fair amount of potassium out there. Phosphorus, though, we have mined most of the easy, what you might call the low-hanging fruit. It's getting harder and harder to find. What are we going to do? What are we going to do when phosphorus is rate limited? We can't find enough. Okay. Maybe someone will come up with a process that they can artificially manufacture phosphorus fertilizer, but it's not nearly as easy to deal with as nitrogen. Nitrogen's all over in the air. 80% of the air is nitrogen. So there's plenty of nitrogen here. There's not plenty of phosphorus. And if that becomes limited, suddenly our agricultural output could take a dive. And then we could have millions, if not billions, of starving people because we can't feed them because we don't. We're limited with the phosphate fertilizers. Now that's extreme, and it may be way out there, but I think there's a blurb in the book on that. That might be a decent paper topic if someone's interested. Okay. So anyway, that's your phosphate appetite. And then the halides, there's lots of that. Halite is sodium chloride, fluoride, I think it's sodium fluoride. There's plenty of other minerals out there that deal with the chlorides, the fluorides, the bromides, and the iodides. And then your native elements, gold, silver, copper, diamonds, sulfur, elemental sulfur. Those do occur, very rare. That's why they're fairly valuable. Sulfur is not as valuable as the others. Copper less so than silver and gold, but still pretty valuable. Okay, so there are your minerals. In the classification, silicates, 92%, non-silicates, 8%. The silicates, ferromagnesium silicates with iron content, non-ferromagnesium silicates without iron content, and your clay minerals, which are reformulated, very small particle size minerals. Then your silicates. Now, there's a problem here. Pretty sure we were saying there are 8 classifications. I only see 7 there. Let's go back and see. 8 groups of non-silicates. Carbonates, sulfates, oxide, yeah, there's 8. Oh, they left off the hydroxides. They didn't list those here because they're a little more rare. So that's the one they're missing, hydroxides. So there really is 8, not 7. Okay. Now, here's some pretty pictures of some of those. And both of these are exactly in your text. Okay. Guess what kind of silicates these are? How do these differ from those? The color. What makes the darkness? Iron. Ferromagnesium silicate. Compare the dark colors of the ferromagnesium silicates. Augite to the right, okay, hornblende to the left, and biotite in the middle, okay. To the light-colored non-ferromagnesium silicates, these are your mica, which are these down here, these two. Mica, and you can almost imagine this. You can pull the mica off in sheets. It's rarely a two-dimensional crystal with very weak bonds between the sheets, strong bonds within the sheets, so you can pull them off in sheets almost. In fact, when the U.S. was growing, people were moving west, and they started going into the prairie. You know, starting maybe with Illinois, but then moving on west, Nebraska and Kansas and certain places. The further west you got, the fewer trees you had. And trees used for wood, you know, the wood from trees is usually what people built houses with. Well, running out of those, so they started building what we call the soddings. They would just take those great grasses that grew all over the prairie grasses, really strong root systems. They would just pull up bricks of those roots and use those bricks to stack and build their houses. Great insulation, okay? Really thick walls and strong, you know, pretty good stuff. But they didn't have any sand, nor did they could afford to bring glass from out east. So what they would do, they found mica in the area out there. They would pull off sheets of this and have that as their windows. It wasn't transparent, it was translucent. You couldn't really see through them easily, but it did let light through. And so many of their early windows were made from micas. Okay, pretty much a two-dimensional crystal. High in potassium, by the way. And then you have white and pink orthoclase, that's top and center. These are white, that's the pink orthoclase. Okay, and if you go back to remember what orthoclase is your potassium feldspar. Okay, so the micas are high in potassium, so are your orthoclase. Okay, quartz, that's this one. You can tell. You see those crystals? Beautiful hexagonal crystals there. That's quartz. And compare that to the dark colored ferromagnesium, non-ferromagnesium. Reason for the darkness? Iron. Iron. Okay. All of them silicates. All right. Now we get to on page 440, which is where that table was, and the pictures are actually on 441. We are going to look at some of the physical properties of minerals. Okay? We know what they're consisted of, the ordered bonding of their minerals, of their elements and compounds. But what are some of the physical properties? Okay? This is starting on page 441. I mean, the title is on 440, right at the bottom of the page, and then you start seeing these on 441 and follow it. One thing that's pretty obvious, you just picked it out in the previous slide illustration there, the color. Now, to identify a mineral by its color alone is not very easy to do because it can be influenced by trace impurities, minor little amounts of impurities. Like I said, I have a sample of a rock down below that has quartz crystals. You can tell they're quartz crystals, but it's pink. It's not clear like quartz is supposed to be. Just very minor amount of impurities change the color. Okay? So color isn't the best way to classify. It is one of the physical properties, but it's not the best classifier. Better than that is something called streak, which has to do with color, but what you do is get a really rough material like sandpaper might work on some, corundum, which is a harder type sandpaper, would work on some of the others. You might have to go to even diamond impregnated sandpaper, which is pretty expensive. That might be useful on some, but when you rub the mineral across that, the streak that's formed when the mineral is finely powdered, that color is much more useful in classifying than just the obvious color. More consistent than the color alone. You're dealing with the color, but it's the color of the finely powdered streak that you have when you rubbed off some of that. Next is hardness. That is your resistance to scratching, and that's why I kept naming different things. If your mineral is hard, sandpaper isn't going to give you a streak, because if the mineral is harder than quartz, it's not going to work. So it's a resistance to scratching. There is a scale called the Mohs scale. Okay, Mohs hardness scale. It uses 10 test minerals with increasing hardness, and that's how you classify. Here are those 10 minerals. The very softest of your minerals is called talc, which is I think it's a form of a mica, a very, very soft mica. That's Mohs hardness 1. You can't get much softer than that. And some of you ladies probably have used talcum powder before. Ooh, isn't that soft feeling? Okay, it's baby powder, talcum powder. Okay. Number 2 is gypsum. Now this isn't pure gypsum, but what we sometimes we don't have any in here called sheetrock. Okay, that's the more common name for it. That's a brand name. Is gypsum board. Gypsum sandwiched between two pieces of basically cardboard, and that's the stuff in the middle of gypsum. And that's soft. You easily cut with a knife, with your fingernail. That's gypsum, number 2. Calcite's number 3, That's, you can't scratch with a fingernail, okay? And that's your calcium carbonate. Pretty crystals, by the way. I'll show you some of those when we do the lab. Fluorite is the next. That was one of your halogens, remember, fluorite. Apatite, that phosphorus mineral, was next. That's number 5. Pretty hard stuff, but it can be scratched with other things. Orthoclase. Remember what orthoclase was? Orthoclase was your potassium feldspars. Okay? That's number 6. Quartz. That pretty mineral, clear most of the time. That's number 7. Sandpaper, mostly quartz. Topaz, which is a semi-precious stone, that's number 8. Corundum, harder than sandpaper, that's number 9. Diamond is the hardest, by far. Nothing is harder than diamond, okay? I don't know if we've synthesized anything to be harder than diamond. It's just an incredibly hard material. Now, if you have diamond, it'll scratch anything. If you have, say, quartz, it'll scratch anything below it, but won't scratch anything above it. Okay? So that's what the scale does. The hardness of some common objects, sometimes used for comparisons rather than the actual test mineral. Some of the common objects, approximate hardness, are the fingernail, which is in between gypsum and calcite. That's why I said the fingernail will certainly scratch gypsum, but won't scratch calcite. A copper penny, which really isn't copper anymore, but it used to be copper, but now it's alloy with copper and something else in it, a cheaper metal. But that is about a 3.5. That would be between calcite and fluorite. Ordinary glass is usually 5 to 6 because you have different grades of glass. That would be between orthoclase, apatite, and orthoclase. And then, a pocket knife blade is right also in that range, 5 to 6, depending on how hard the steel is. Okay, so if you can scratch it with a pocket knife blade, then you're 5 to 6. Okay, won't be able to scratch quartz with that. Okay, topaz you could, corundum you could, and certainly diamond you could. Okay, that's Mohs hardness scale. Pretty good classifier. How hard is this mineral? More physical properties. The crystal form. Now, we talked about some of those arrangements, 6 basic groups already mentioned, related to the internal arrangement of the atoms. We're not going to do much with that, okay? However, the next we do, the cleavage. And this are the planes where you're easy to break and the other planes very difficult to. It's the tendency of minerals to break along smooth planes. Now, what was the hardest mineral?
The diamond.
Diamond. And yet, if you are a really talented professional, they call diamond cutters. There's probably few occupations that can earn a bigger income than they can, okay? The diamond cutters, because this is a precious thing, and if you hit the plane just right, you can shape that diamond to have multi-facets so it really glitters and stuff. However, one slightly false move and you might fracture it. Big, beautiful diamond, one false move, not the little diamonds, okay? Not nearly as valuable as that one big diamond. So the cleavage and the fracture go sort of hand in glove. Cleaver is the tendency to break along smooth planes. Fracture is the irregular nature of some broken surfaces. So when you do your next lab, basically, you're going to be doing these physical properties, okay? And the cleavage fracture is slashed. So you can either talk about the cleavage and or talk about the fracture. Some minerals won't cleave very well, but will fracture. Some fracture will cleave extremely well. It's pretty difficult to fracture. Okay? So you'll talk about those two together. Another is called luster. Now that's different from color. This is the surface sheen that the mineral has. If it has that metallic kind of look to it, that's a metallic luster. If it's the milky kind of pearly looking, that's a pearly luster. If it's watery looking, like you can always see through it, that's a vitreous luster. And there are a few others. You'll see those when you run into them. Now here's the one physical property that's probably the best classifier you have out there. Density. What is density? Mass to volume ratio. Okay? Just about every naturally occurring material, and even some man-made materials, have a unique density. Okay? Unique density. Okay? So if you can determine the density of a mineral, you are really well along the way to figure out exactly what mineral that is. Now, because mass has a unit of grams or kilograms, volume has a unit of cubic centimeters or cubic meters, one or the other, then density has units. Grams per cubic centimeter, kilograms per cubic meter. That's a huge unit, so I don't usually use that. Some people do. It's SI. But rather than that, some people will use specific gravity. It's the ratio of the mineral density to the density of water. Well, guess what the density of water is? 1 gram per cubic centimeter. So if you had something with, say, 4.3 grams per cubic centimeter as a density, divide that by 1 gram per cubic centimeter, and basically you just lose your units, and you wind up with 4.3 without any units. That's specific gravity. It's the ratio of the mineral density to that of water. It basically is dimensionless, whereas actual density has dimensions, grams per cubic centimeter or kilograms per cubic meter. Now, sometimes in the U.S. system, we use a weight density, which is pounds per cubic foot. That's not really this kind of density, mass density, that's weight density. Now, there are two main factors that contribute to the density of the material. One of these is the kind of atoms making up the mineral. Okay? And if you think back to the elements, those are the kinds of atoms that you saw prevalent in Earth material, in Earth's crust, and in the whole Earth. Silicon was pretty prevalent, especially in the crust, really prevalent, like more than a quarter of the crust is made up of silicon. Those are very, lightweight minerals. But when you get down into the core, what's the most prevalent mineral element? In the core. It's the most prevalent element. Iron. Exactly, iron. So that's a dense material. So the types of atoms, here again, remember we said iron makes it dark colored, lack of iron makes it light colored. Well, iron makes it high density, lack of iron has a low density. Lighter color, lighter density. Two different kinds of light. Okay? But there's another factor. How are the atoms arranged in the crystal lattice? There is one, yes, it's a mineral called osmium. It is really, really dense. But osmium itself is not that heavy of an atom. It is a heavy atom, but it's not nearly as heavy as several below it, but it's denser because the atoms of osmium really stack together in a dense pattern, whereas the others are a bit further apart, so they have a lower density. So the kinds of atom, iron versus no iron, and the packing of the atoms, densely packed or loosely packed in the crystal lattice. Okay. One kind of crazy example, these aren't minerals, but just to give you an idea. What is the only material, naturally occurring material, whose solid density is actually lighter than its liquid density? Most of the time, a gas is the lowest density, liquids are next lowest, and then solids are the densest. One naturally occurring molecule whose solid density is actually less than the liquid density. And I bet you I could almost come up with an example of this in 3 different locations in this room. It'd be all right if I borrowed your cup. Okay. Would you want to take the lid off? Yeah, I'll handle it. Okay. You drank most of the liquid, didn't you? What else is in there?
Ice.
And if I filled this with water right now, I'm not going to, where would the ice go? It would float up. That's solid water. The liquid water goes down. Water, the most prevalent compound on the surface of the planet.
So it's water weight.
Huh?
I'm so serious.
Yeah.
So water itself.
Yeah. It's when it freezes, it becomes less dense because the water molecules are held together by that hydrogen bonding. I haven't talked about that yet, but and that really holds them tightly together. In fact, water should be a gas. It shouldn't be a liquid at all. But that hydrogen bonding really holds those molecules close, but they slide past each other, but they're really close together. When it starts freezing and has to go into that crystal structure, they have to get a little further apart to fit in the crystal structure, so therefore it floats. One of the few, if any, naturally occurring materials that when it goes into a solid phase, it gets less dense, not more dense. Because of that one little feature, life exists on this planet. Because if that were not true, go anywhere up north or way down south, where in the wintertime it typically freezes, then every lake, every river, every stream would freeze from the bottom up, and life would not be able to exist. What happens now? Water freezes and the ice goes up, leaving liquid water and air gap underneath. That's why fish and everything else can live even if it's under ice. Whereas if it was like everything else, no life on it.
So that's like why sea otters still be alive.
That's why, and because they can live.
That's the environment.
But yeah, it's an ecosystem. We can't exist outside of everything else. Thank you, water, for having that quirky nature. Okay. All right. The packing of the atoms also influence, and the molecules influence the density. Okay, so here are a few more physical properties, and these are things that we talked about earlier. This is gypsum, and that's, remember, 2 on the Mohs hardness scale. Your fingernail's 2.5, you can scratch gypsum fairly easily. Okay? Here is quartz. Those are the pretty crystals you see there. See them popping up there? Hardness of 7. So hard, even if you had a metal file, you can't scratch it. Because remember, the metal in the knife blade, that's 5 to 6 on the Mohs scale. Quartz is 7. You can get a file of that. Work yourself silly and you're never going to scratch the quartz with a metal file. Okay? Now, those are the physical properties of minerals. Frankly, folks, that's your next lab. Okay? And we'll be doing that in a computer room somewhere. we'll find that. Don't try to get 256, which is the orientation classroom, if there's no orientation class down there. Okay, now before we move on to mineral forming processes, there's a couple more really nice pictures in the book. Well, it actually is an updated picture of what you have here. This is mica here, I mean not mica, gypsum, and they're scratching it with glass, not your fingernail, or it looks like glass. I can't tell for sure. And then the quartz is even a nicer looking picture of crystals here than what you have there. They both are pretty nice. Okay. They do have, on example 17.1, they give you the mass of a crystal. They tell you it's the mineral augite, which, if you recall, is a ferromagnesium silicate, meaning it contains iron. Okay, they give you the dimensions of this mineral, and therefore you can, that's length, width, and height, so you can calculate the volume. They gave you the mass, and it says its cleavage causes it to break into a rectangular solid. What is the specific gravity? Basically, that meant because it's a rectangular solid, you could use, you could measure length, width, and height easily. That was sort of out of it. And then it said, what is its specific gravity? So you have the mass, multiply length times width times height, you get the volume. Mass divided by volume is its density. Divide that by the density of water, which is 1 gram per cubic centimeter, and you get 3.26 is the specific gravity. 3.26 grams per cubic centimeter is its density, but just 3.26 is its specific gravity. Then 17.2 is a potassium feldspar, non-ferromagnesium silicate. I bet you it has a lower density, lower specific gravity. Sure enough, it does, 2.56 compared to 3.26. Okay. That difference is the difference in the minerals, in the atoms in there, iron versus no iron. Okay, how are we doing on time?
308.
It's what?
308.
308. Okay, we're doing fairly well then. I'm not going to have time for a lab, I don't think, but okay. So, moving on to mineral forming processes. What makes these minerals? How do they come into existence? Okay? Basically, the formation, minerals are formed in 2 liquid environments, being the most common. These are very different liquid environments, extraordinarily different liquid environments. The first is water solutions. Okay? The crystals form from highly concentrated ions. Okay. Now, find a stream out there, a creek, a river, whatever. Okay? That water that's there has run off the soil, and as it ran off, it dissolved stuff, okay, into the water. You know, because water is a great solvent. It dissolves lots and lots of things. So a lot of your salts and things like this, some minerals actually get dissolved in the water. It runs down, mixes with other water, keeps running down, finally gets to the sea somewhere, Gulf of Mexico, the Atlantic Ocean, Pacific, somewhere, gets to the sea, and now combines with all the other water coming in with dissolved salts. Okay, once it gets into that big body of water, the ocean, especially near the equator, you start losing the water. It evaporates away. So your salt content builds up. So now you have higher and higher concentrations of your ions. Okay? Now, with higher concentrations, that tends to get heavier and it starts sinking. Okay? And even in the Gulf of Mexico, remember the Gulf oil spill? One of the reasons that was so hard for them to control is because it was a mile or more down. And at those depths, you're down to very close to freezing temperatures. In the Gulf of Mexico, near the equator, no, you're freezing temperatures that deep because there's no light gets down there, no heat gets down there. So now, okay, think about this now. Have any of you ever made hot tea? Okay? Is it very difficult to sweeten your hot tea with sugar?
I prefer to put sugar in hot water because it melts faster.
Okay, yes. Sugar melts faster in hot water than it does in cold water.
Yeah,
Iced tea, try to sweeten that with sugar. It just settles to the bottom, doesn't it? So the hotter the liquid temperature, the more ions it can hold. And the deeper it goes and the colder it gets, the concentration of ions gets greater and greater and greater. Well, at some point, those crystals start coming out of solution. Okay? Because they can't support, the water can't support it anymore. Concentration increases, the water can't hold it any longer, and the crystals form and come out. Now, the slower that process is, then, and the less mixing you have, the bigger and bigger you can grow your crystals. Okay? And you can get some pretty good sized crystals out of that. So that's one way. Water solutions, high concentration of ions, they come out of solution at some point, either because of concentration, the water is being evaporated away, or the temperature is dropping and it can't keep it in solution as easily anymore. So that's one liquid, water. Very different liquid, magma. What in the world is magma? Melted rock.
Yeah.
Absolutely. Now there's one difference between magma and lava. Magma is melted rock below the surface of the earth. Once that melted rock gets to the surface, then it becomes lava. Okay? So where it's located determines. But molten rock from which minerals can crystallize. It can happen below the surface of the earth or above the surface of the earth. Okay? We will classify our minerals according to that. Lava is magma that's forced to the Earth's surface. Once it reaches the surface, it becomes lava. Before it reached there, it was magma. Okay. Now, again, things depend on temperature. Some of your minerals are going to come out of magma solution at very, very high temperatures. Most of your ferromagnesium minerals come out at very, very high temperatures. Okay? Others, it will cool greatly before they come out. A lot of your non-ferromagnesium minerals come out at very low temperatures. Deeper you are, the higher the temperature, the closer to the surface, typically the lower. Unlike water, the deeper you go, the colder it is. But in the Earth's, the solid Earth part, the deeper you go, typically the warmer it is. Pressure, temperature, friction, and you're getting closer to the hot core that's down there. So, I've already mentioned these. The important factors here, temperature, here and here, pressure, mostly here, time. Okay? Is this happening quickly? Is it happening slowly? Is your temperature changing slowly? Is it changing rapidly? That's going to affect your crystal formation. And the availability and concentration of ions in solution. The more concentrated, the bigger crystals you're going to get. The less concentrated, you'll probably get very small crystals. Now, let's go to this time issue. If a mineral cools too quickly, it really doesn't become a mineral. It becomes a glass. A glass is a rapidly cooled solid lacking the crystal structure. In other words, it cooled so quickly it didn't have time for the molecules to get into the right positions in the crystal lattice to form your crystal.
Excuse me, I just heard that glass is also breakable.
Yes, it is. And if you look at how it breaks, it shatters. It doesn't form clear crystal planes, cleavage planes. It all sorts of shapes in there. That's indicating it's not got a crystal structure. Okay. The other thing about glass, you can heat it up and mold it. Okay. Globes. Have you ever seen any glass blowers? What's that?
My friend does it.
He does it. Okay. I bet you can make some beautiful stuff too, can't he? Okay. There was one time when my wife's family went down to the beach. It was Seaside or one of those places. A company was set up there near a parking lot, and they were blowing glass. And you just heat it up, and then the glass starts taking all these amorphous shapes, and you could blow and get it into really unique surfaces. That's because it wasn't really a crystal anyway. It was a glass. Rapidly cools out, and that's how you make your glass. You cool it quickly. Have you ever watched him do that when he's through with the shape? Dunks it underwater, doesn't he, or something like that. Very rapid cooling. It goes to a solid right away. Doesn't have time to form the crystal structure that the quartz had. That doesn't look good, does it? Makes me think my bulb's about to go. I hope not. Those are expensive. Okay. So, minerals formed at very, very, very high temperatures. There's a guy named Bowen. I think they probably give his name in here somewhere. N.L. Bowen. They don't give his name, just his initial. He conducted a series of experiments, and he came up with this reaction series. Okay? It's the silicate crystallization sequence, which comes out at the highest temperatures, which come out at the next highest, and down to the coolest. The ferromagnesium silicates crystallize at higher temperatures. They come out of the magma solution much sooner at higher temperatures than the others do. The minerals are crystallizing later, are progressively richer in silicon, less rich in iron and magnesium. That's what ferromagnetic stands for. It doesn't have anything to do with magnetic. That's magnesium magnetic. Okay? Here is the sample from the Bowen's reaction site series. Olivine, remember I said that's in the mantle. That comes out at the highest temperature, then your augite, then your hornblende, and then your biotite. Now notice the color is getting lighter and lighter as you go, because the heaviest iron content are up here, less here, biotite. If you go back and look at that picture of biotite, it's sort of grayish looking compared to the olivine, which is very, very dark. Okay? But on the non-ferromagnesium side, the temperatures aren't the same, but the series is. You have your plagioclase feldspars up here, your calcium plagioclase here, sodium plagioclase here. Then your potassium feldspar down here, that's your orthoclase, I think it is. Yeah, plagioclase, orthoclase. And that's your potassium feldspar. Then you get your muscovites, which are sort of like your micas and things like that. And then you get your quartz. The quartz comes out at the very last, the very coolest temperature of your non-ferromagnesium out of solution. And as long as that comes out slowly, the temperature change is very gradual, you can get the big, beautiful quartz crystals. If that happens more quickly, you get little bitty crystals. If it happens too quickly, no crystals at all. It forms the glass. Okay? If you've ever been someplace where there's volcanic materials. Some of that lava that cooled very quickly forms what they call volcanic glass. The rocks are really shiny looking. They almost look like they could be glass. They're jet black color, but they're really pretty. Those are glasses. They're not actually crystals anymore. Now let's talk about glass for a minute. We mentioned it several times here. Our house where we live was built late 1929, early 1930. It was finished in 1930, started in 29. We looked it up and found that out. And it may be back then they didn't, and that was right before the recession, the Great Depression and stuff. And it may be that they just didn't have good quality control of the glass manufacturing process, and I don't know. But anyway, just about every window in our house has this waviness to it. You look out and things aren't, it's not pure flat glass like this. You can definitely see it. You can tell which panes have been replaced because those are flat glass, And sometimes the waviness is horizontal and sometimes it's vertical and sometimes it's horizontal. Just depends on what's it. Makes me think it's a process that was the issue. But if you go to very old places like the cathedrals in Europe and some of those stained glass windows, now they don't let you get near them and they don't let you do this, but people have measured those, and very typically the glass at the top is incredibly thin and that at the bottom is thicker. Because guess what? That glass is not actually a solid. It's not a crystal structure. There's no crystal structure holding it in place. Those molecules are really slowly, over time, moving past each other and gathering at the bottom. Glass is a supercooled liquid. It's not really a solid because the molecules do move. A crystal, to be a solid, it has to be fixed in that crystal structure. And it doesn't move. Nothing moves from there. But because it's a glass, they actually do slide past each other incredibly slowly. Like over thousands of years, they move a little bit, But it's a supercooled liquid. Okay. So I blame some of the waviness in our house in that it's, what did I say, 1930. So it's about 80-year-old glass. So that accounts for a little bit of the waviness, but probably most of it is that it was not that good a quality glass to begin with. I don't know. But I think it's neat. Okay. Now, minerals formed at normal temperatures, formed at the Earth's surface in contact with oxygen, carbon dioxide, and water. Those are the three most common things. Those will be your carbonates from carbon dioxide and water, your sulfates, oxides that form strictly with the oxygen, the halides that forms with the halogens over on the column 7, and the sulfides, sulfur that doesn't combine with oxygen but just is pure sulfur. Okay? Except for the oxides, those oxygens right here. Okay? These have substantially lower hardness and lower specific gravities than the minerals formed at higher temperatures. Why? Because those at lower temperatures, it's almost all silica. You don't have the heavier elements in them. They've already gone out of solution at the higher temperatures. Okay? Oh, did y'all need that a little longer?
Yes, sir.
Okay, sorry. Stop me if I go too fast. I'm not famous for going very fast. Boy, that bulb is just going crazy.
I hope no burns.
I hope so too.
I heard those good burns.
That what? We could probably go next door and use their protection. I do use this a lot. And if you go back to the Bowen cycle, you notice they're getting lighter colored, lighter colored, lighter colored. Those at the bottom didn't even have any color at all. Your quartz and micas, muscovite, those that have any color at all. But also the hardnesses are less, except for the oxides. They can be really hard and have high specific gravities because they could be iron oxide, they could be other oxides. All right, we got it?
Yeah.
Okay. Now, little blurb here. They don't do as much in the newer editions as they did in the old on altered minerals. But it's not a insignificant thing, so we'll do it. Exposure to different environmental pressures, temperatures, or chemical solutions can change former minerals into slightly different ones or newer ones. Now, especially if the pressure is increased, the temperature increased. Now, certainly if you mix some chemicals in with it, that could change things major anyway. But the increased temperature and pressure actually changes from one mineral to another. And in the next section of the chapter, when we start talking about rocks, we will see this happening big time there. Okay? Now, generally these alterations occur at temperatures of 150 degrees, above 150 degrees, and above 2,000 atmospheres of pressure. That is a lot of pressure. Okay? Are we under any pressure now? Do you feel like there's any pressure on you? I'm not talking about school pressure or expectations and things like that. Well, it's pretty okay, right? But actually,
we don't feel it.
Yeah, we may not feel it because there is exactly one atmosphere of pressure above us. Because we have all this air, and believe it or not, air has weight. Okay? All this air going for miles up there is weighing down on us. Okay? And that's why, if you were to cut yourself, the blood actually comes out rather than sucking air in. You would think pressure would. We're actually pressurized so that we can withstand the pressure above us. Okay? Now, based on that, I would contend, I haven't seen any studies on this is my personal opinion, that one of the most dangerous jobs any human has ever attempted to do would be a spacewalk. Okay? A spacewalk. Those astronauts that go out. One thing in particular, way back when our shuttle system was operating well, the Soviets had the space station. We didn't have a very successful space station. We put one up, but it didn't last too long and it crashed into the sea somewhere off Australia. Okay? We weren't too successful. Soviets, however, had a successful space station that stayed up there a long time. And what the Soviets did typically was send up unmanned cargo ships, rocket ships up there, and they were computerized and supposed to dock at the space station, and then they get the supplies off and then jettison it off and space jump. Okay. However, there was at least one that malfunctioned pretty badly. I don't know why or anything, but it actually came in too fast, and it basically crashed into the space station. And it damaged a lot of the structure, and the cosmonauts who were in the space station had to go into a tiny little area, volume in their secure place, and they were confined in there for quite a long period of time, and that couldn't have been very pleasant. Okay. Well, they had no way, because they didn't send unmanned things up there, and usually if they were wanting to change out cosmonauts and astronauts too, they hitched a ride on our shuttle fleet. Okay, so what we did, we sent up a series of shuttle missions to go up there and do some of the repairs to the damaged space station, so those poor cosmonauts could get out of that little tiny little area and move around there. So those guys went up there. I think it was mostly guys. There could have been a few women that did it too. And they went out there where jagged metal, torn and ripped, by that collision that happened with that, unmanned spacecraft, and did repairs to that. Okay, and if you think about that, that was incredibly dangerous, because what are they in? They're the big old bulky spacesuits. Well, there's a couple of reasons why they're big and bulky. One, they're silvered so that reflect, because out there in space, all that radiation is out there. Cosmic radiation, gamma radiation, X radiation, all that. Our atmosphere shields all that from us. Just a little bit of UV radiation gets in, and that's what causes wrinkling, skin cancer, cataracts, and things like this. You don't want to get UV ray. I mean, people go out there, sun worshippers, and get their tans and stuff. You're killing cells. That's what you're doing. Okay, so you don't want to do that. Well, our atmosphere protects us from that. Out there, there's no atmosphere. You're exposed to all that. So number one, the space suits are designed to deflect most of that harmful radiation away. Good. The other thing is they have to be pressurized, because we're used to living under 1 atmosphere of pressure. Now think about what 1 atmosphere of pressure is. 14.7 PSI. What does PSI stand for?
Pounds per square inch.
Pounds per square inch. A square inch is about the area of your thumb joints, the 2 thumb joints together. That's about a square inch. Think about how many square inches it takes to cover your body, and multiply that by 15. How many square inches by 14.7 or 15? That's a lot of weight. That is an enormous amount of force. Well, that's the pressure in our bodies pushing out. We're probably 15 or more pounds per square inch pushing out, because we can stand the pressure. There's astronauts up there floating around with all that jagged metal and stuff, trying to do repairs to the exterior of that Soviet Soyuz space, station. Jagged metal and stuff. If one of their spacesuits had gotten caught on a jagged piece of metal and ripped it, there goes all their pressure that's pressurized their suit, and there goes all the pressure inside their body out. Probably mostly through the eyeballs and nose, but also through the skin. There goes spewing into space. All the gases and the liquids in their body. That's why I say can't be many things that are more hazardous than that. And yet they were very successful. They got the space stations back up and running, and they could move around So those unsung heroes in my mind to be risking that and to do those kind of repairs with a big old bulky and gloves, and how in the world they did it, I don't know. Okay, but they worked at it awfully hard. Okay, so what my point was, that's 1 atmosphere of pressure that's over us right now to give us 14.7 pounds per square inch. That's a lot of weight. Okay, now go down 10 meters. Okay, 10 meters is about like a 3-story building. That part of the building over there, 3 stories. Well, this is about 1 meter, 2 meters. That would be about 3 meters. So 3 stories with some space between. That's going to be pretty close to 10 meters. 3-story building goes that far down underwater. You've added another atmosphere of pressure. Okay, go down another 10 meters, another atmosphere of pressure. Every 10 meters you go down adds another atmosphere of pressure. Just think how deep you'd have to go to get up to 2,000 atmospheres of pressure. That's a lot of pressure. Well, you have that underneath all the rock. Water is fairly low density. Under all the rock, you can build up that much pressure. And at very high temperatures. And then you're going to alter some of the minerals to form your garnets, epidote or epidote, I don't know how to say that, your talcs. I would think that would be at very high pressure there. Graphite, actually graphite at fairly low pressure. Take that graphite under very high pressure, and you get, at high temperatures, graphite. What is graphite? Anyone know? Well, remember one thing. I know I had it, my pencil. I don't know what happened to it. Oh, there it is. It makes a soft lead, but that's mixed with kaolinite. Without the kaolinite, it's really so soft you can use it as a lubricant, graphite lubricant, right? Really, really slick, fine, okay? Put that under a lot of pressure and temperature for a long period of time, that becomes diamond, which is the hardest material out there. So you go from being a lubricant to being the most abrasive material you can ever have, which is just about on the opposite end of the scale. Serpentine is one of those asbestos minerals. Put this under a lot of pressure, you can change some of these things to much harder rocks. Those are your altered minerals. We'll talk about this more on the rock section. We are in the mineral section now. Okay, let's look also at the ore minerals. Remember, those were the non-ferromagnesium, the least found. These are mineral deposits generally with economic value, often found in veins. Okay, and these veins are thin, flat bodies of mineral material. Red Mountain. Down here, what's the one not far from here where they had some furnaces and Sloss furnaces in downtown Birmingham, but there's one somewhere around here somewhere that's Tannehill. Tannehill, I think, had some of those. Okay, well, basically, they mined most of the easy to get to material, and they quit mining then. But left over from crystallizing magma, flushed away in hot water solutions, redefined. Examples: pyrite, iron sulfide. I said it wrong before. Iron sulfide, fool's gold, and then chalcopyrite, which is a sulfur of copper and iron, which I don't think is goldish color. You would think the copper would make it even more so, but it's the iron pyrite, iron sulfide, that makes fool's gold. Sulfur is yellowish color, iron is darkish color. Somehow, with the chemical forming of pyrite, it becomes gold color, which is bizarre. All right, that was the first. Oh, I'm sorry. Okay. That's the last slide in the mineral part of the chapter.
We got like 5 minutes.
Okay, maybe this will be a decent time to go on and start marking the roll for the second half, and then we'll just take a quick break then. Okay, Tiara didn't make it in today. Been a while since we've seen her. Matthew's still here. Takirius we'd never have seen. Dante is still here. Ty is still here. Demetrius is sick. Stexany is still here. Justin's still here. Demetric is still here. Ishmael didn't make it in today. Darren's still here. Zachary's still here. David didn't make it in today yet. Sarah's still here. Max is still here. DeAndre's still here. And Chris is still here. Okay. I probably shouldn't have been recording all that, but I did. Okay, those who have finished marking this, you can go on and start your break now. Try to get back in less than 5 minutes. I will definitely begin, if I can, in less than 5 minutes. So try to get back. I'll leave this up for those people who are still recording. At least get up and do some side straddle hops or something, you know, move around, get blood flowing, whatever.
Don't forget to stop recording.
What's that?
Don't forget to pause the recording.
Yeah. I can really pause it now. The slide will stay up there. And we'll go from there. All right. Now, I don't know if this is half the chapter, but it's the other half of the title, Rocks, beginning in 17:4, page 444. What are rocks? What's the physical science definition of it? It's an aggregation of one or more minerals. So you can't have a rock that's totally made out of the same type of minerals. Or more minerals, more than one type of minerals. And perhaps some other materials. Minerals are very specific. You had to have these characteristics: naturally occurring, solid, crystal in structure, you know, all the things that had to be there, inorganic, had to be there to be a mineral. But a rock can contain some other materials that are not necessarily minerals. Okay, but they will contain minerals, one or more minerals. Minerals are physically combined to make rocks. Physically connected. Not chemically necessarily, but physically connected, combined to make rocks. Most rocks are, since most minerals are silicate minerals, most rocks are silicate minerals. They probably should have contain silicate minerals. Very seldom will you have absolutely pure limestone that only contains calcium carbonate, okay? You'll usually have some silica mixed in with the limestone, so it will have some silicate minerals. There are some classification schemes, 3 main groups based on how the rocks were formed. The 3 groups are igneous rock, sedimentary rock, and metamorphic rock. Now we're going to go over each one of these in detail, but for right now, let's give just a general idea. What word do you almost see in igneous? If you change the E to an I and change some of the stuff out here. Ignite! Okay? Think formed with fire. In other words, rock that was formed from molten material. Igneous rock. Okay? Sedimentary, what does that make you think of? Things settling out. Sediment. Yeah. Things coming out of solution into layers and then forming rock that way. That's sedimentary rock. Does anyone know what the word metamorphosis is?
So like changing?
Changing, big time, okay? What's the classic example of metamorphosis? A hairy, fuzzy little caterpillar becoming a butterfly. That's sort of the classic definition of metamorphosis. Changes everything. Changes the way it looks, changes its structure, changes everything. Morph means to change. Metamorph is big change. Okay, big change there. I just made that up. I think that's sort of what it means. Okay. So we'll look at those individually later. Okay? Remember, rocks are made of minerals, but can contain some other stuff as well. Okay? And mostly containing silicate minerals, because most of the minerals, 92% of the Earth's crust is made out of silicates, so it's not at all surprising most rocks contain significant quantities of silicate materials. Okay. And the minerals are physically combined, not necessarily chemically combined. A chemical combination usually changes stuff. Physical combination just basically sticks them together, okay, in some way, shape, or form. All right. And we'll look at the three main groups individually, starting with igneous. Everybody got it now? Okay. Starting with igneous rocks. Now, igneous rocks were formed, remember, from molten material, from magma, which is molten material. Now, here's a problem I have with this. It's formed from lava above and magma below, okay? Because once it reaches the surface, magma becomes lava. So if it's above the surface, it's lava, and below the surface, it's magma. But it was magma originally anyway. So formed from magma, either above or below the Earth's surface. Now, let's just think about that for a moment. If it formed from magma below the Earth's surface, generally that's going to be cooling more slowly. But if it forms from magma above the Earth's surface, that's cooling really quickly. So keep that in mind. Okay? Now, here's another really interesting statement. All rocks, sedimentary, metamorphic, were at one time igneous rock. Because guess what? At one time the planet was one big ball of liquid. Okay? It was molten all the way through. Because the forming process, when all those collisions were happening and that kind of stuff, and the radioactive stuff being fired out of the sun and stuff like that, it was all, at one point, igneous rock. Because it all cooled from some type of liquid molten material. But not all rocks are currently igneous rock, but at one time their components were. Now, here's what I was mentioning up here. The cooling rate determines several things. And one of these things, the main thing, is the texture. And what do we mean by that? A mineral that cools slowly, which means rock that cools slowly too, generally are going to be larger crystal sizes. If it cools rapidly, tiny crystal sizes. So the large crystal size will have a very coarse texture, whereas the fine crystal size, cooled very quickly, will have a very fine texture. So that's what it means. Cooling rate determines the texture. All right. Another way we classify the igneous rocks, were they formed above or below the Earth's surface? If it was below the Earth's surface, then we call this intrusive igneous rock. And here's the thing to remember on that. Inside the Earth, intrusive, okay? Below the surface of the Earth. That was your intrusive igneous rock. Formed beneath the surface, and because it was beneath the surface, the slow cooling produced generally larger crystals. Generally produced larger crystals. Therefore, the rock was coarse-grained. Remember, the cooling rate determines the texture. Coarse-grained rock that cooled more slowly because it cooled inside the Earth more slowly than at the surface, so it would be larger crystal size. Whereas that was exterior, it exited the Earth's surface. That's extrusive igneous rock. That's formed from lava, not magma, but it's now become lava, on the surface. Now, get what we mean by surface. Surface of the Earth would be like the Kilauea volcano that was erupting in Hawaii like crazy, and all others, that stuff that comes out on the surface. But this also means through the rock.
The mantle surface?
What?
The mantle surface, like the surface up under us, like how Earth got different layers,
Right.
And each layer has its own surface. So the mantle surface, which is what the lava and the magma being that comes as lava, is that what you mean by that surface?
Okay,
Come
well,
through the tectonic plates.
second.
Does it come through the tectonic plates?
Yes, it will be doing that, and we'll talk about that in the next chapter. It's exactly where it comes from. But the point is, not all of this is at the dry surface of the Earth. It could be under the ocean coming up. That's going to cool really quickly, too. So, surface of the crust, let's put it that way, whether that's in air or in water. Both of those are going to be extrusive igneous rock formed from lava on the surface of the solid Earth, whether it's underwater or not. That's rapid cooling. Small crystals, unless it's so fast at cooling that it forms a glass. All right, now here are two interesting, to me anyway, fairly interesting. This is a piece of rock that we call granite. Granite is coarse grained. You can almost imagine rubbing your hand over that, feeling the fairly large crystals. Not huge, but fairly large. There's a pretty good sized crystal. There's one. There's pretty good sized crystals. They're pretty good size. You can see the crystals in there if you look closely. Okay? So it's coarse grain. I can't read that. I know it's in the book. I just can't read it there. Coarse grained igneous rock composed mostly of light colored, light density, non-ferromagnesium minerals. Okay? However, there are some dark colored in there. Those are ferromagnesium minerals. Remember, a rock is made up of many kinds of minerals. The very lightest color are probably quartz, okay? And the sort of brownish color are other types of non-ferromagnesium, but maybe your feldspars and some of those. But then the dark little specks that you see there probably are biotite. Some minerals are biotite, some of quartz, some of feldspars, some of a variety of things. Okay? The Earth's, I can't read it, something area. Yeah, continental areas are dominated by granite, and the rocks with the same mineral composition as granite. So it doesn't have to be granite, but it could have the same mineral composition. Now, this is a piece of obsidian. Okay? Notice how slick and glassy the surface of that is. You don't see any grains of anything in there. That's because this is I'm sorry.
Bless you.
Thank you. The chemical composition of this and that are identical. And yet nothing could look further from each other than that. This was minerals formed slowly, large crystal-sized, coarse-grained texture. This was formed very quickly. Same chemical composition, formed very quickly, and actually didn't form crystals, and so it formed this glass. It's called obsidian. Same chemical composition as granite. The obsidian has a different texture because it does not have crystals involved and is a volcanic glass. The something fracture, I can't read that. Is that in this book? Yeah, there it is. The curved fracture surface is common in non-crystal substances such as glass. So there, it's a different piece of obsidian there. Now, I don't know if any of you are Game of Thrones fans. I've never seen the series that's on some sort of channel somewhere. I think it's on cable somewhere. But I have read several of the books. And obsidian was the type of sword that you had to use on some of the creatures to kill. And I thought, this is a bit bizarre. Well, the whole thing's bizarre. But anyway, that's obsidian. Same chemical composition as granite, very different in appearance. Because this is slow-cooled, large crystal, intrusive igneous rock. That's not a mineral at all. That is glass. Same composition, though. Chemical composition. Very, very different. So, how do we classify the igneous rock? We've already seen some. You have intrusive, extrusive, okay? You have large crystal, small crystal. You have all this stuff. So, how do we classify? Two factors, mineral composition and texture. Those are the main two factors. So, in the mineral composition, you either are non-ferrous or ferrous. Non-ferrous composition is, and here's that up the chart here. All right, this is a fairly busy table, but it's pretty neat in how it puts all this together. The non-ferrous composition is on this side. Hardly any iron in it. The iron is basically in this. They would have made it black, but then you couldn't see the writing. So they made it green. There's nothing green about it, but that's your ferromagnesium minerals, okay? On this side, the non-ferromagnesium. So they're low in density, light in color. Quartz is almost colorless. The potassium and feldspars are a light sort of tannish. The sodium and calcium-rich feldspars, which are your plagioclases, they're a bit browner in color, and then the dark stuff is your high iron content. Biotite, not as dark as amphiboles, not as dark as pyroxenes. Olivines are some of the darkest, highest concentration of iron. Now, if you're paying close attention to this, these were not the terms we saw. We saw biotite and olivine back in the Bowen series. If you don't mind, let me flash back there. Oops, there it was. What we had there was augite and hornblende, okay? Well, these are various names for similar materials, okay? Had olivine, which is the darkest, the heaviest, the densest. Biotite, the lightest and the lowest density, came out at higher temperatures, at lower temperatures. But there it was augite and hornblende, and here they named pyroxenes and amphiboles. Okay, amphiboles closer to biotite, pyroxenes closer to olivine. Okay, so now. Low density, light in color. The most common, and these are in the continental portions of the Earth's crust, the most common is granite. Granite is coarse grain. There is another fine grain. These could occur as the sort of in between obsidian and granite. Rapid cooling, but they did form crystals, just fine grain crystal. That would be rhyolite, okay? That's a rock. It's not a mineral, but it's made out of these various minerals. Notice there's some biotite. Remember those little dark specks you saw? That was probably biotite, okay? The darker brown was your plagioclases, mostly sodium rich. Your potassium feldspar, the orthoclase was a light brown, and the whitish were the mostly quartz. Increasing silicon content, decreasing silicon content. Increasing potassium and sodium, this way increasing calcium, magnesium, iron and magnesium. Now, they don't ever mention nickel. If there is any nickel, it's that way too. It's not common on the surface of the Earth. Okay, now, the ferromagnetic materials, those on the darker end, the heavier end, these are greater density because of the iron content, darker color because of the iron content, and typically the more common of these is basalt. Now, the basalts are typically formed when your magma comes to the surface underwater. Those will form your basalts. You can have them form on the surface, in air, but mostly more so under the water when the magma comes to the surface there. However, you can also have very dark materials forming under the surface, larger quartz size, and that would be your gabbros. Okay? Now, we have a countertop at the two-bedroom bungalow we have over in Georgia on the farm that is dark colored but large crystal size. You can see the crystals in it. Now, I'll show you some examples of basalt, or at least I think they're basalts, of some floor tile that we put in our master bathroom when we redid that here in Birmingham. And I'm pretty sure that basalt because it's fine crystal, fine grain, so that would have been basalt. But in our countertop, very dark color, just like the basalt, but much larger crystal size. That's gabbro. I don't have any of that. It's over at Georgia. They didn't leave any samples of them there. And then in between, you have these others, which are, I've seen the names before, but they're not as common. The most common here, the coarse grain, light colored is granite. The dark colored, the fine grain, is basalt. Those are the most common. Basalt being your ferromagnesium, granite being non-ferromagnesium. However, it still has some biotite and maybe a few amphibole minerals in it, crystals in it. Okay? Make sense? Beat it to death? Okay. Whoa! And that's it for igneous rock. The picture that they show in your text of granite has more biotite and possibly some amphibole in there too because they're really dark sections. A bit heavier on the plagioclase, the darker tan, with some of the lighter tan, which would be your orthoclase, and really fairly little quartz. There is some white in there, but not very much. Okay. I think I'll go back to, just as a re-emphasis, so I'm coming back to this. When we were doing our upstairs bathroom, what had happened, the shower had some cheap little tile that someone had put in probably in the 50s or somewhere, and we just could not keep the grout clean. It just kept getting dark, and we could scrub on that stuff, and it seemed like it did no good. And my wife finally said, let's see what's wrong with this. Let's change this and make it something that she liked better. So we got our carpenter, to do some of the work, and then we had a pretty good tile man also, and he came in, and we had gotten the materials. We got sort of a white colored stuff for the floor, beige kind of stuff for the tiles on the walls of the shower, and the floor was kind of in between the two. And, it had some things, but it was pretty bland, I guess. He said, go get me some black granite to put in to spice up the floor a little bit, because the floor was mostly white material. And I said, sure, and I went to the store to see if I could find some black granite. They said, yeah, here's some. I found some and took it home, and he said, yeah, that's good. And then he put little strips and squares in it, so it really made it pop. And he did some other things with the shower, really made it nice too. We never would have dreamed of that. He was really, really creative. and for really cheap jobs, it looks incredible, okay, because we're cheap, okay. But he was very good, and just with simple things, he did it. Well, later, I was telling my niece about it, and she was working on her master's in geology and geography, mostly geography, at Eastern Kentucky. And she said, there's no such thing as black granite. What? She said, no, there's no such thing as black granite. Well, then within the next year, I taught this course for the first time. And sure enough, I found out granite, to be granite, has to be light in color. And then I found out, well, that probably what we have there, because it's fine grain, is basalt, not granite. But the guy called it black granite. It is. There's no such thing as black granite. If I'd only taught the course a year earlier, I wouldn't have made that mistake. But she corrected me, and she had a big time doing so. Okay, so anyway, that was basalt. So just to let you know, no such thing as black granite. Okay. And in fact, I think the guys who did the kitchen cabinet over in Georgia, I wouldn't be surprised if they said, oh, and we'll put black granite on your circle, on your thing. No such thing. It was gabbro. Coarse grain like granite, but dark in color. All right, so let's get to sedimentary rock. As we said, this is formed. Okay. Now we're going to talk about this in a later chapter, but we got to bring it up here too. Okay? All rock breaks down. All rock, in some sense, sort of dissolves away a little bit. So no rock lasts forever. Okay? No mineral lasts forever. And as the rock is breaking apart, maybe by physical means, by chemical means, by biological means, it's breaking up, little pieces of it separate. And as they separate, they get carried away. And at some point, those pieces settle out somewhere, maybe in the bottom of a river, the bottom of the ocean, in a cave, at the bottom of a stream. Somewhere they settle out. Okay? Now, these particles can be big particles like gravel. They can be smaller particles like sands. They can be really small particles like silts, or they can be incredibly small particles like clays. And they can be mixtures of all those. So these are the sediments that come out. And over time and pressure, these sediments then sort of reform themselves into rock. That's what sedimentary rocks are. Okay? Accumulation, the sediments, and there's two kinds. Physical sediments, particulate sediments, accumulations of silt. Think of silt as flour. Very small particle size. It's really slick. You don't feel any grittiness at all. That's silt. Sand is gritty. Okay? You can feel it. But it's still small particle size, but you can feel the grit. Clays are incredibly tiny. You can't possibly feel any grit on them either, but they're much smaller than silt. And they're actually reformed materials. Silt is just sand that's been ground down even finer until it's made of powder. Okay? But clays actually dissolved and reformed and made tiny, tiny little crystals. Okay? But these materials settled out, mostly settling out of water, and we'll talk about how they form later. The second type of sediment is not particular, but chemical sediments. We call this, the physical sediments we call plastic sediments, accumulated from rocks at various stages of breaking down. What they're calling sediments here, sand, silt, clay, settled out of water, these are plastic sediments. Okay? Now, they love this table. You're going to see it here, you're going to see it later, you'll see it again, you'll see it maybe 3 or 4 times, and there's lots of good stuff in it. We're talking about the clastic sediments now. Later when we talk about chemical, we'll see the same table again. The clastic sediments are either larger than sand, like gravel, and that's called conglomerate or breccia. Okay? And the difference there is whether it's rounded or angular. Okay? And you'll see this in one of these tables. Okay, I've got to find the table for you here. Tell me they left the table out of the text. No, there it is. There it is. It's conglomerate has the rounded fragments, breccia has the angular fragments. So that's the difference. But they're basically gravel, something larger than sand that's been fused together, cemented together, and formed a new rock. And the materials you see in there are great big chunks of gravel, and they're conglomerate if it's rounded gravel, breccia if it's angular gravel. Okay? Or you could have plastic sediments that are sand. That forms sandstone. And I have some samples of that you'll see in the lab next time. And we also have plastic sediments that are either silts or clay. Now, silt, remember, is flour-like texture, very, very smooth. Okay, that would make siltstone. And I wonder sometimes if that's what they call soapstone. You know, that really it feels like soap. There's such a slick texture to it. The clays would form claystone, and the other name for that is shale. Okay, you can't tell any kind of a grit or anything in that, and that's very much in sheets, basically. We'll get to the second part of the table later. But those are your plastic sediments. Larger than sand, in other words, gravel, conglomerate if it's rounded, breccia if it's angular. Sandstone, you can feel the roughness there. The siltstone and claystones, shale, smooth as soap almost. I mean, just really, really smooth. Okay. Now, here's how we classify those materials. This is where you see the rounded is conglomerate, breccia is angular. I knew it was in one of these tables. Okay. How you classify these various size of particles. Okay. Clay basically is dust. Okay. It's finer than dust. Okay. That would be many clay particles stuck together would be dust. I mean, here's what a clay technically is. I don't think I have a dime on me. I used my dimes when I bought lunch today. But I do have a penny. Penny's just a little thicker than a dime. Okay? That is about 1 millimeter thick. Approximately. A dime would be closer to it. So let's imagine you take that penny and slice it into 1,000 equal slices. I can't even imagine that. 1,000 equal slices. With 2 of those little slices, it's called 2. They don't use this term here. 2 microns. Okay? 2 of those together would be the largest dimension you'd ever find on a clay particle. You're not going to feel that. You're not going to see that. Even with the most powerful optical microscope, you'll never see a clay particle. They're way too small. Only with an electron microscope can you see an image of a clay particle. They are tiny. Tiny, tiny, tiny. So that's smaller than dust, finer than dust. And that's the largest dimension on a clay particle, is 2 microns. Okay? Anything less than that is a clay particle. And that would make claystone when it's settled out. Silt, that is literally flour-like material. Okay? No grittiness at all, but there are particles there. You can't see the particles of clay. That would be silt. That's in between clays and sand. When they're gritty, that's sand. Okay? Now that's up to 2 millimeters. So the largest sand particle would be like 2 dimes together. That would be the largest dimension there. Anything larger than that would be gravel. And that's mostly what makes up conglomerates and breccia. anything larger than that, 10 inches or bigger, you call that a boulder, okay? You don't usually have that big of, that is your rock. You don't usually find that in a rock, sedimentary rock. I can't imagine. So anyway, anything larger than 10 inches is a boulder. Smaller than that is gravel. Gravel can form sedimentary rock, and that would be conglomerate or granite. Okay, so that's the clastic sediments. These are the particles that make up the clastic sediments, except boulders. Boulders is the rock of its own. Okay, then on the other side, the chemical sediments. Okay, this is when the water, which is usually the culprit here, has broken down the rock. It's been dissolving portions of the rock. Okay? For instance, calcium carbonate dissolves to a certain extent. Everything dissolves to some extent. So the water is dissolved, the rock material, and now it's in solution. Formed from dissolved rock material, not broken down rock material, dissolved rock material. The three sedimentation paths here. Okay? Now, here's what the chemical precipitation from solution. Does that mean anything to any of you? Okay, I didn't think so. Here's what we mean. When I took my first chemistry class at Georgia Tech as a first quarter freshman, the first lab we did, they issued all the stuff, and you counted all your materials, and you got all the stuff together. And the first lab we did, though, they gave us a solution of silver nitrate. They gave us another solution of sodium chloride, salt and water. Okay? Silver nitrate is soluble in water, and it's a clear liquid. You couldn't see there was anything there. Sodium chloride dissolved in water. You couldn't see anything there. It just looks like water. But they told you it was silver nitrate, sodium chloride. So what they had you do was drop a drop of the sodium chloride into the silver nitrate solution. And immediately what happened, a white powder, a white substance came out. What that was silver chloride. Silver chloride was not soluble. Silver nitrate was, but silver chloride wasn't. So you had silver and nitrate ions here, you had sodium and chloride ions here. When you mix them together, when the silver came in touch with the chloride, they precipitated out, meaning they fell out. It fell off a precipice, precipitated. That's what water, rain is, precipitation. That's what snow is, precipitation. That's what hail is, precipitation. It's not what dew is. Dew just happens, and frost just happens. It's a surface contact. Something that's falling out, that's precipitating. So chemical precipitation from solution. So say you have some water coming in from one stream that has something dissolved in it, water coming in from somewhere else has something else dissolved in it. When they get together, they precipitate out another mineral. Okay? That is chemical precipitation. So that's one sedimentation path. It came out of solution, and that formed a chemical sediment. Another is crystallization from evaporating water. Now, have any of you ever went to boil you some beans for supper, okay? Or peas or corn or something. And you wanted to get your water boiling before you put your vegetable in, and to give it a little more taste, you put some salt in there, right? So you got your water boiling, but then the phone rang, and you ran in and got to talking with your girlfriend or your boyfriend or your mom or somebody, and you lost track of time, forgot you had the pot on the stove, and when you went back in, all of the water had evaporated away, and you had a crust of salt at the bottom of the pan. Well, that salt was initially dissolved in the water, but when the water evaporated, the salt didn't evaporate, and it was left. Well, that's crystallization from water evaporating off. Okay? And then the third, and this is rather strange kind of title here, biological sediments. That could be just about anything. Basically what they mean from that is things that, not crystals necessarily, but things biologically, like bones or shells or things like this that sort of fallen out too. Now you can't classify those as clastic because they aren't sand, silt, clay. They're not minerals themselves. They're other biological pieces of something that came out. And that could, I think, probably include things like coal. I don't know for certain if that would classify here, but that's the other sedimentation process. We're not going to mess with that much. We're going to deal mostly with the first two. Okay? Now, so here we have the second part of the table. I told you you're going to see this table over and over again. Chemical sediment, one of these is calcite. Okay? The particle was dissolved, calcium carbonate was dissolved in water, and it kept building up, okay? Dropping out, getting colder and colder, and after a while the water couldn't hold it anymore, it started crystallizing. And by the way, calcite, the crystals are absolutely beautiful crystals. Really sharp cleavage planes. Really sharp, neat cleavage planes. You'll see some examples of that. And what I didn't realize until one of the students brought me some of these crystals, he was actually a coal miner. He said, yeah, the calcite happens around coal. So there you had biological sediments with chemical sediments right next to each other, and they fused together in places. You'll see samples of that. Okay? So that's calcite. Another is, and that, by the way, the rock that's formed by calcite crystals is limestone. Limestone has other stuff in it, probably some quartz, probably some other stuff, but it's mostly calcite crystals. Another chemical sediment would be dolomite. Dolomite is calcium magnesium carbonate, a combination of the two, and the rock that's formed from that is called dolomite. Okay? Really clever with that. Actually, there's a town near here called Dolomite. What is it? A little bit north and maybe west of here? Not too far from Mulga, is it? Somewhere up there is a town called Dolomite. I'm guessing they have dolomitic limestone there. Does anyone know it? Okay. Now, I know this is a part of the course, but let me just give you a little bit of a background on that. What is limestone typically used for? Does anyone know it? Or lime? There's lots of uses for it, but agriculturally. Anyone know it? And we don't do that much of it here, but they do some. Over in Georgia, they got to do it more. Georgia soils are formed from granite, acid igneous rock, so their soils are pretty acidic, and they've been overfarmed for years, so they tend to build up acid. They don't grow as good at crops. Okay? So what they do, they grind up limestone, which is calcium carbonate, and spread that on the field. That raises the pH. It was very acid, it raises it to more neutral. We always lime the fields over in Georgia about every 3 to 5 years just to keep the pH up. Otherwise, it got too acid, they wouldn't grow good crops. Well, calcium carbonate, limestone, your regular lime, that's a great acid reducer, but all the soils already have plenty of calcium in it, so it isn't improving the fertility of the soil that much. It just raises the pH, drops the acidity, so it makes it a better environment for plants to grow. The roots are happier, everything's happier. But dolomitic limestone, because it has calcium and magnesium, magnesium's a lot harder to come by, and actually the plants need the magnesium for another purpose. Does anyone know what? I've got to sneeze, sorry.
Bless you.
Gesundheit.
All right. Now, does anyone know why plants need magnesium? as opposed to calcium. They need calcium too, but they don't. There's plenty of calcium always there. But magnesium, those little green leaves there, what makes them green? A chlorophyll molecule. You've heard of chlorophyll? That's the thing that acts to take energy from the sun into the plant so it can separate the carbon dioxide from the oxygen and use the carbon to build sugars and later fats and proteins and other things. But to do that, you've got to have that chlorophyll. What is a chlorophyll molecule? It's a little claw of organic material with, in the middle of the claw is the magnesium molecule, the magnesium ion. That's why plants need magnesium. So if I'm doing in the garden or something like that, if I have a choice, I'm going to use dolomitic limestone. Sometimes it's hard to get that, but you can only get calcitic limestone at Home Depot or somewhere. You can't find any dolomitic. You have to use something to drop the pH. But if I can, I'll get dolomitic. It's not as good a limer, acid reducer. It takes longer time because it's a harder mineral, but it adds more magnesium to the soil. And by the way, this is another aside, that chlorophyll molecule with a magnesium in the middle, the same structure is found in humans, except instead of magnesium, it has iron in it. And you know what that structure is called? Hemoglobin. That's what carries the oxygen from your lungs to the part of the body that's going to metabolize and do the work, and then carries the carbon dioxide back to the lungs over and over again. So that essential thing in humans and in all animals, hemoglobin, just like chlorophyll, the essential thing in green leaves that does the energy transfer to make the green leaves use the energy from the sun to make their sugars. Pretty incredible the way we're put together. The claw is the same, almost identical. But another chemical sediment, sedimentary rock, is gypsum, which is calcium sulfate. Another one would be Epsom salt, which is magnesium sulfate. Another one is halite, which is sodium chloride that's come out of solution. We just call that rock salt, okay? Which I guess is very similar to what you use when you're making ice cream in the summertime, right? Rock salt. And if you've ever noticed that at the end, there's some brownish and blackish and gritty type stuff that didn't dissolve, probably quartz. Because the rock contains more than just the mineral. It contains other stuff as well, okay? Including biological sediments, okay? Some of that black stuff could be biological sediments. All right, here are some samples of sedimentary rocks. This is limestone, okay? It's pretty clean. Sometimes it's a lot dirtier looking than that because algae and other stuff loves to grow on it because it has that. It's a sedimentary rock formed underwater, sometimes with the remains of marine organisms. Right here you see what? A shell. Okay? The shell right there in the limestone. So there's the biological sediment. It also showed up in here. Otherwise, this is very fine calcium carbonate crystals in there. You don't see the crystals, but they're there. And there's the brachiopod fossil, or the shell right there. Here's another piece of sedimentary. That's chemical sedimentary rock. This is clastic, particulate. This is sandstone. You can almost see the grittiness in there. Piece of sandstone, sedimentary rock, formed from consolidation of sand grains into a solid rock. This sample of iron banding was from Tasmania, Australia. Neat place to be. This has higher iron content because it's redder. There's a higher iron content, which is redder. There's higher iron content. These others have very low iron content. Sedimented out at different times from different sources. And then there was some pressure that bent, we'll talk about this later, bent that sedimentation, because you know it settled flat and then some sort of stresses made it bent. We'll talk about that in about 1 or 2 chapters later. This is what's the overall name? I've forgotten it. All they say is larger than sand. This is gravel. These are chunks of gravel. This is a rock with chunks of gravel in it. And this is breccia because all the gravel is angular, not rounded. Okay, so this would be breccia. When I think rounded, I think pea gravel. All those are almost spherical, you know. So that would be, if that was in here, that would be conglomerate. This is breccia because it's angular. Okay. This sample is from gravel size or smaller fragments from Colorado. Probably left over from a glacier. Probably the pressure of that glacier on the gravel and stuff. And you have, we'll talk about this later, cementing agents in between here that hold it together. And that made a new rock. Sedimentary, clastic sedimentary rock. Clastic sedimentary rock. Breccia, sandstone, chemical sedimentary rock, limestone. Okay? Now, there's a blurb at the top of page 446. Cost of mining mineral resources. Okay? It's a pretty good little article, and there's some questions to discuss. We're not going to discuss those, but they may be questions that might lead you to a paper topic if you haven't already chosen one. Might not. I don't think I would choose something like that, but you may find it very interesting and something you want to pursue. There's example 17.3 is an interesting example in that it's using the table that's in figure 1713 to try to come up with possible classification of rock. I found it pretty interesting to do. It takes a while, and you have to do some interpretation of it, but it's probably well worth the time and sort of fun to do too. And 17.4 is another one like that. All right. If you look at, and this isn't in our slide set, I wish it was. Here's that table again. They love that table, okay? This is chemical sediment, calcite, limestone. This is clastic sediment. The sediment is sand, so it's sandstone. This is plastic sediment, larger than sand, gravel. And this happens to be breccia because it's angular. But in your text, there is a different piece of breccia shown here. In fact, 2 pieces. That first piece, the one that's sort of reddish in color, I'd come pretty close to calling that conglomerate because it looks like those pieces are more rounded and less angular. But I guess there's just enough of angles in there, they call it breccia. The one on the right is obviously angular, so go with that. Okay. The figure 1717 in your text, we don't have a picture like that in the slide set. That's limestone. Now, I think I've, in many ways, tried to sort of drive my wife crazy. That's, I guess, my job as a husband. But especially when we're driving on the road and you have these road cuts. And I'll say, oh, look at that limestone. Look at it, and literally, you can pay a lot of attention to road cuts, the banks on the side of the road. Now, when they brought in stuff, you can't really tell much there. But there are other places you can see what natively is there, and you'll see limestone on many of the sides of the road when you're driving, through a place that they've cut through the existing structure. So enjoy that. start paying attention. This is limestone, one of these. And even though that's a chemical sediment, you can still see the layering here. A lot of times you can't with limestone because it's chemical, but that's what you're seeing in 1717. Okay. Now we're ready, and this is the bottom of page 448. But they give it a whole slide here. This process, and this is for sedimentary rocks, lithification. Litho means rock. This is the formation of rock, the rock forming process for sedimentary rocks. Two main parts. Remember, the sediments are brought in, usually by water, and someplace or another they deposit. And then more sediments on top of that, more on top of that, more on top of that. And over years, decades, centuries, millennia, whatever, piled up, more pressure, sometimes more heat. Here's the things that are going on there. The first part is compaction. As more layer goes on top of more layers, on top of more, the ones at the bottom are getting compacted more and more and more. Now what's happening there, when it's fragments, there's a lot of pore space in between the fragments, okay? If it's brought in by water, a lot of that pore space is filled with water, okay? And brought in. And when they're compacted, the water is squeezed out, okay? At least most of the water is squeezed out. Some of the remaining water that's in there probably has stuff dissolved in it. And as that water then seeps away or evaporates away or whatever, it leaves some of that other material, and that's the cementation. The spaces between the sediment particles, whether it's sand, silt, clay, gravel, whatever, are filled with a chemical deposit, probably left over by the water, okay? And, was that a question? Okay. And the chemical deposit binds the pieces together. That's the cementation. So you have compaction, which forces the particles closer and closer together, leaving less pore space, but in that pore space, you have some type of material there that tends to cement it together. So you have compaction going on with cementation. Okay? Here's the illustration of that. When the first deposit comes in, there's lots of pore space in between the particles. When more overburden is on top of that, it crushes it downward, compacting it, removing some of the pore space, squeezing it out. And when it squeezes out, it loses some water, but the water leaves behind little chemical sediments here, which tend, when they dry or get more temperature or something, they tend to cement those pieces together. These could be incredibly small clay particles. They could be very small silt particles. They could be sand particles. They could be gravel. That looks like gravel to me, but it can be any of those. And that's what forms your sedimentary rock, at least the classic type of sedimentary rock, particulate rock. Okay? Did everybody have that? I'm sorry. I'll leave it up a little bit longer. Okay. Don't let 5:15 pass without stopping me, because at 5:15 we pause, we stop, and we take our test on chapter 16. We've got about about 25 minutes. But I forget
29.
29 minutes, okay. I said about, so okay. My watch is a little fast, so try to. All right. People still copy. Okay. So lithification process is the process, rock forming, that's what that means, lithification. Rock forming process of clastic sedimentary rocks. Clastic meaning particles. You have to have the particles in here. The particles are what are compacted, squeezing out the water, and cementation is in the dissolved material that's left over from the water, hardens, dries, heats, whatever it does to stick or cement those particles together. Cementation. Everybody got it? All right. Now we're ready for our third type. Now, before we turn the page on this, there is a nice blurb about asbestos. Now, y'all may find part of what I'm going to say next hard to believe. Because when you think asbestos, what do you think? Good, bad, or ugly, what?
Cancer.
Cancer, bad, okay? Now, I can remember when asbestos was counted as a wonder material. Oh, one of the best things to happen. Why was that? Asbestos is fire retardant. So, boy, the more stuff we can make with asbestos, the better. It was a great insulator, okay? So we can insulate pipes with this material, and it will never catch on fire, okay? It's wonderful stuff. I can't remember how many years ago it was. It may have been a decade or more. Someone had gotten some of these old clips from some really old television shows. And I think the one I remember this was George and Gracie, Burns and Allen. I don't know if y'all even know who that is. George Burns and Gracie Allen, they were a married couple. They were funny. They were one of the best comedic teams I've ever seen a show from. But this was ancient. Okay, they were old when I was very young, so that's how far back they go. And someone was showing some of these, and the advertisement that came on in the middle of their show was on asbestos tile, and how wonderful that was to put that in your homes, because then you would never catch fire. Well, today we know asbestos, or at least some asbestos, is carcinogenic, cancer-causing, causes asbestosis. That's probably not cancer, but it's a really serious disease that breaks down your lung material. Not good at all. Okay?
How they find out?
What's that?
How they find out that it's
It was years of using it. They started seeing cases of it and then traced it back and said, ha, that's the culprit. Unfortunately, that's what happens a lot of time. It's only after decades of use that we find out, hey, this isn't such good stuff after all. Here is the really sad part. A lot of the asbestos, naturally occurring asbestos, is not cancer producing. Only certain types of asbestos are. A lot of them are not. So here we have a lot of really good material with all these fabulous qualities that don't cause cancer, but we won't use it because it has the A word, asbestos, and people are scared to mess with it. So anyway, it's a good blurb to read. Someone may want to do a paper topic on that. That would be pretty interesting. On the top of the next page, using mineral resources. Earlier they said the cost of mineral resources. Now this using mineral resources has several questions there you can think through. Okay? Another pretty good blurb to read. They have a little concept supplied saying collect dry sand from several locations. Use magnifying glass to determine the minerals found in each sample. Well, at least come up with good guesses. I don't know if any of you have ever seen or heard of the sand paintings that certain Indian tribes do out west that are just absolutely incredible. They collect sands from different sources, from very different and brilliant colors, and then they put these together ever so carefully into paintings, but they're actually different colored sand particles. And they have made some incredibly beautiful designs with that. That's an extension of this. Okay, let's go to metamorphic rock. What did metamorphic mean? Anyone remember? Metamorphosis? Oh, it was a long time ago. Maybe an hour, hour and a half. Changing. Big changing. Metamorphic rock. Rocks that have changed in some way majorly. Now, I said the caterpillar to the butterfly, that's sort of the biological classic metamorphosis. There was one author, and I right now cannot remember his name, pretty famous author. He's weird as all get out. German, if I'm not mistaken. It wasn't mine, but it was a compatriot of his about the same time that wrote a book, and the title of this little book, or novella or something like that, is Metamorphosis. And the theory behind it, there was this jerk. That's basically what he was, a jerk, okay? He crapped on people, he just messed them up big time, and he didn't care, okay? And one morning he woke up, and he was a cockroach, okay? And that's the thing, it's some sort of esoteric, there's another word for it, thing. I can't remember the author, he's a very famous author, but the name of his book is Metamorphosis. The guy changed, not that much in character, but in appearance. Anyway, to a cockroach. So, what is metamorphic rock? Previously existing rocks that have been changed, metamorphosized, big time, morph means change, by heat, pressure, or hot solutions into distinctly different rock. Okay? We'll look at some of that. Okay? What are the causes? Most of the time associated with geologic events. Movement of the crust. So suddenly there's been a lot of pressure, a lot of heat, a lot of activity. This may have brought up some of this hot solutions, or other things. And this combination of stuff has changed. And literally what's happening. Remember, your rocks and minerals are made out of this crystal structure, okay? And when you put a lot of heat and pressure on crystal bonding, you change the bonding. That's what happens between graphite and diamond. You change the bonding, so you change the characteristics of the identical material to totally different substance. Graphite, a black, slick, lubricant, to diamond, a clear, really beautiful crystal made out of pure carbon, both of them. Yet the bonding change changed everything. That's what's happening here. The heat, pressure, and hot solutions are changing the bonding structure. That could be from moving of the crust. It could be from heating and hot solutions from the magma intrusion that's made its way up, and suddenly everything is a lot hotter. The temperatures must be high enough to cause recrystallization. That's what I was talking about. The crystal structure has changed, but not hot enough to melt it. Because once it melts it, it becomes magma again, and then when it re-solidifies, it's not metamorphic, it's what is rock that comes from molten material. Say again? I thought someone said it. Ignite? Igneous. Okay. So there's a fine line there that it has to practice, to meet. Here's a few examples. Remember when we were talking about clay that's formed in layers and that forms shale. That's sedimentary rock. That's claystone. Okay, shale. Layers of shale. It's fairly soft rock. It's fairly not really usable for very much. But if it undergoes a lot of pressure and temperature change, that changes to slate. That's a metamorphic. This is a clastic sedimentary rock. This is metamorphic rock. Slate, on the other hand, is hard. What do they use slate for? Maybe many things, but one thing, and it comes in sheets. You can divide it into sheets really easily. Cut those sheets into about the size of a towel. Slate roofs.
So the stuff that's on top of the roof.
Yes, that's quite up the slate.
Right over those things called that you stay.
Okay, now the towels, that's formed by heating. You know, if it's curved and that kind of stuff, like they have in Spain and a lot of areas in Europe. That's tile. Slate or flat things, usually sort of a greenish color. Our church is South Highland Presbyterian Church, and the old part of the church still has slate roof. Okay.
Oh,
yeah. It looks just like tile, except it's actually rock. It's heavy, but it lasts a long time. Okay. Now they can get loose, and you have to go up and do it. That's slate. We have a piece. Evidently, there was a huge fire in New Orleans sometime early in its history, and it jumped from building to building on the asphalt, they used cedar shakes as the roofing material, and that stuff burned like crazy. So they decided they didn't want that to happen because the fire jumped from roof to roof to roof, and those cedar shakes just burnt like crazy, and so everything was destroyed. So what they did, they imported slate from Pennsylvania, and a lot of the old buildings in New Orleans have those slate roofs. And my wife got a piece of that when she went to New Orleans once. It had something on it and told that story. Well, slate, if it undergoes more pressure and temperature, it becomes a really hard rock called schist. Okay, be careful how you say that. Okay, and that becomes even harder than slate. It isn't as easily divided, and then you can add more heat and more pressure, and it becomes nice rock. Okay, the G is silent here. It's called nice. And that, do you remember that chunk of rock we saw very early in the chapter? We'll see it again, and it had those curves in it and layers, but it was all, and we said it's one of the oldest rock going. You probably weren't here, I don't remember that. But anyway, that's a piece of nice, okay? Really old, hard, metamorphic rock. Well, then you add more heat and more temperature, and I said the same thing, more pressure. How does it become granite again? Granite is what kind of rock? Ignite. Igneous rock. It's actually melted and went back to being. All rock was at one time igneous rock, and if you keep adding heat and pressure, at some point it's going to melt again and go back to being igneous. Okay? So that's with classic sedimentary rock, shale, mudstone basically, or claystone. Limestone, on the other hand, is chemical sedimentary rock. If you add heat and pressure, it changes that calcite crystal structure from limestone, which is sort of a soft and porous kind of rock, into one of my favorites, marble. Hard, sometimes even brittle rock. And that marble is then metamorphic rock. It
15 minutes.
Say again?
15 minutes.
15 minutes? Oh, okay. To go. I thought you said it meant 5:15. Okay, so the marble is metamorphic rock. But if you add more heat and more pressure, what does it become? It melts. And it goes back to being melted calcite, and it's going to re-crystallize as a igneous rock. So let's go to another. This is back to a classic sedimentary rock, sandstone, and you add heat and pressure, and finally you fuse those sand particles into a new crystal structure, which is called quartzite, metamorphic rock. Okay? You add more heat and more pressure to that, more heat, finally you melt it, and when it comes back again, it's not quartzite, but quartz, which is igneous. Okay? Back to being igneous rock. And then you could even have a fine-grained igneous rock, such as rhyolite maybe, or something like that. And you add heat and add pressure and add heat and pressure. And now you've reformed the crystal structure there until it becomes a schist. Just like the shale became a schist, okay? It's a changed rock, and that add more heat and pressure, and it becomes nice, another nice rock, okay? And more heat and more pressure finally melts it, and it comes back as granite, an igneous rock. So it went from sedimentary to metamorphic to metamorphic to metamorphic to igneous. You went through the whole rock cycle right there, a few times over. Chemicals, sedimentary, metamorphic, ultimately back to igneous. Classic sedimentary, metamorphic, back to igneous. Igneous, metamorphic, metamorphic, back to another type of igneous. This is a coarse grain. This was fine grain. Okay? Changed the nature of it because it actually melted and came back. Okay. Does that make sense? Oh my goodness. I'm running out of steam. I think we've got time for this one. So let's look at the classification of this metamorphic rock. Boy, all these rocks have different classifications, don't they? The main way we classify metamorphic rock is its foliation. Now, what in the world does that mean? What's another word that sort of sounds like foliation? Foliage. Like the leaves on the tree. That's foliage, isn't it? Leaves on the tree. Layers. Any of you in sort of an artsy type thing that you put together a portfolio of your, right? Those are sheets of showing your work. Folio, sheets. That's what foliation is. The alignment of flat crystal flakes into sheets. We saw that in shale going to slate. It became flat crystal plates metamorphosizing into sheets. Okay, caused by the pressure on the parent rocks, the original rock, like this slate, the shale going to slate. Okay, so the original rock was the shale, and then it became slate. Goodness, I can't talk. The rock cleaves along the planes between the aligned grains, and you get the foliation. Okay? Or non-foliated. The parent rock consists mainly of one mineral. Grains are not aligned into sheets, but are three-dimensional, and therefore you get non-foliated metamorphic rock. That would be something like graphite metamorphosizing to diamond. Diamond doesn't have any foliation at all. Okay? So that would be sort of an example of that. So that's probably not, yeah, I guess it is metamorphic. Hadn't ever thought about that, but I guess it is. So here's the classification scheme for metamorphic rocks. The non-foliated would be things like your quartzite and marble. There's no sheet-type nature of that at all. Then very finely foliated, that would be your slate. Remember, that came off in definite sheet. Finely foliated, your schist was not as well finely foliated, so it's, but it was foliated. And then coarsely foliated, barely foliated, that was your nice rock, okay? And then the non-foliated is back to quartzite and marble, okay? So we saw all of those. Very finely foliated, definitely break into sheets. Finely foliated, you could break it into sheets, but they're not as evenly or nicely divided. Coarsely foliated, just barely be able to break that. non-foliated can't break it. It's three-dimensional. No foliation at all. So that's one classification scheme for metamorphic rock. Okay? While y'all are doing that, let me bring up another issue. On page 451, there is a person behind the science, Victor Moritz Goldschmidt, okay? Something like that. Swiss-born, but became Norwegian, okay? No wonder he has such a hard name. Chemist who is sometimes called the founder of modern geochemistry. So he studied a lot of this stuff, and actually the stamp is from Norway, even though he was Swiss-born. And quite a good, interesting blurb there on him. Frankly, I'd never heard of him before I taught this course, so pretty good blurb there. If you choose to write on him as your paper topic, this cannot be your source. This can be the idea, source for your idea. You have to get your outside material outside the book, somewhere else, not from the book. A few other people are mentioned here. William and Lawrence Bragg, developing a new X-ray crystallography. I use some of that in my master's research. Max von Laue, he was the one who originally discovered it, and then William and Lawrence Bragg applied it to crystallography. Earlier we saw some concepts of Joseph Gibbs, phase rule, so there's another name. So there's lots of other potential topics you can get out of this one little article. Okay. That was sort of to kill time while y'all were finishing writing. All right, where do we go from here?
We got about 5 minutes left.
5 minutes. You know, we're going to come awfully close. Here's that figure we saw earlier on a smaller scale. So I won't go over that again, except to mention this was the plastic sedimentary rock. This was the very finely foliated metamorphic rock, finely foliated metamorphic rock, coarsely foliated metamorphic rock. This was the non-foliated metamorphic rock, which came from a plastic substance. Okay, this is a sample of marble, coarse-grained metamorphic rock with interlocking calcite crystal. And that means interlocking means they really were jammed together and made some very, very strong bonding there. Very hard rock, sometimes a bit too hard, it's almost brittle. Okay? We'll see some samples of this in the lab. And the calcite crystals were recrystallized from limestone. This is that original picture I was talking about before. This is the gneiss rock. Okay? And this was the very coarsely foliated. You can split this into layers. They're not going to be very flat, though. But the banded metamorphic rock, very, very old. They think about 3.8 billion years. That's very close to when we first started, okay? Probably among the oldest rocks on the surface of the earth. Pretty incredible thing. Now, it wasn't banded like that for the full 3.8 billion years. It probably morphed over time. Big time. All right. And do we have time for rock cycle? Let's not. Yeah. Let's end with rock cycle, begin with that next time. And so next time we'll finish chapter 17. We'll start chapter 18. Okay? And then 2 hours before the end, we'll do the lab for chapter 17. And then the next time, oh wait, anywhere in there we may have the trip to the planetarium. I've got to work that out, and we'll try to do that and let you know by next time. If I find out he wants to take us Tuesday, then I'll put it out on Blackboard as an announcement. So watch that. Okay, and we'll do the rock cycle next time.